At the edge of a black hole lies a boundary so mysterious, so extreme, that it challenges everything we think we know about space, time, and reality itself. This boundary is the event horizon, a point beyond which nothing, not even light, can escape. It's not just the edge of a black hole, it's the edge of physics as we understand it. Here, gravity becomes so intense that time slows to a crawl, space stretches to its limits, and the known laws of nature begin to break down. What happens at this threshold is one of the deepest questions in modern science, a place where quantum mechanics collides with general relativity, where particles behave unpredictably, and where secrets about the origins and fate of our universe may be hidden, waiting to be unraveled. But before we continue, subscribe to the channel so you don't miss out on any of these videos. To understand what happens at the edge of a black hole's event horizon, we need to dive deep into the fundamentals of general relativity and quantum mechanics, two pillars of physics that, in this setting, appear to contradict one another in ways that defy explanation. At its most basic level, a black hole forms when a massive star exhausts its nuclear fuel and collapses under its own gravity. If the mass is great enough, nothing can stop the collapse, and a singularity forms, a point of infinite density, surrounded by the event horizon. But this point is not just dense, it warps the very structure of space-time. And it is this warping that gives rise to the event horizon. Now imagine you are falling toward a black hole. From a distance, an observer watching you would see your descent slow down as you approach the event horizon. They would see you move more slowly, your signals becoming redder and fainter until they fade entirely. To them, you never actually cross the event horizon. You freeze in time. But to you, the experience is quite different. From your point of view, nothing special happens at the event horizon itself. You would pass through it without fanfare, drifting inward as though nothing at all had changed. And yet, you would feel the forces begin to escalate. Gravitational gradients, also known as tidal forces, would begin to stretch your body in ways that feel surreal, pulling your feet and head apart more forcefully the closer you get to the singularity. We'll explore this, spaghettification, later, but for now, we must focus on this paradox of perspectives. Herein lies the profound mystery. From the perspective of a distant observer, information never crosses the horizon, it appears frozen just outside it, encoded on the surface. But from the perspective of the falling object, there is no surface. This is the paradox of the event horizon, it is real and not real at the same time. A boundary in space, and yet only a boundary from the outside looking in. One of the most intriguing aspects of the event horizon is that it behaves like a one-way membrane. It allows objects to enter, but not to escape. Why is this so? Because inside the event horizon, the structure of spacetime is so distorted that all paths, even those that would normally move outward, curve back inward toward the singularity. Time and space switch roles. Time becomes the direction toward the center. You cannot stop moving forward in time, and inside the horizon, that means you cannot stop falling toward the singularity. But what about the physics of that edge? How do the equations describe the transition from outside to inside? According to Einstein's field equations, the event horizon is a null surface, a boundary where the escape velocity is equal to the speed of light. But unlike a surface of a star or a planet, the event horizon has no substance. It has no material you can touch or bounce off of. It is defined purely by geometry. Now consider this. The closer you get to the event horizon, the more time begins to behave strangely. Not just from the point of view of an outside observer, but intrinsically, within the coordinate systems used in general relativity. The Schwarzschild metric, which describes the spacetime around a non-rotating black hole, becomes singular at the event horizon, but this is not a physical singularity, only a coordinate one. By switching to a different coordinate system, such as Kruskal-Zuccari's coordinates, we find that the horizon can be smoothly crossed. And yet, the physical consequences of this crossing remain extraordinary. There is also a thermodynamic aspect to the event horizon. It has entropy. It has temperature. This realization, due to the groundbreaking work of Stephen Hawking and Jacob Bekenstein, implies that the event horizon encodes information. The amount of entropy is proportional not to the volume of the black hole, but to the area of its event horizon. This is deeply counterintuitive. Everything else in the universe scales with volume, but black hole entropy scales with surface area. This fact gave birth to one of the most powerful and controversial ideas in theoretical physics, that perhaps all the information about what falls into a black hole is not lost inside it, but somehow encoded on the event horizon itself. This idea forms the basis of the holographic principle, which we will explore in depth later. But for now, suffice it to say, the event horizon is not just a boundary. It may be the ultimate recorder of cosmic information. But how is that possible if nothing can escape? That's where quantum mechanics enters the picture. The event horizon is not a static, featureless wall. It is a seething, fluctuating boundary where virtual particles can be ripped apart by tidal forces. Pairs of particles are created near the horizon, one falls in, the other escapes, becoming Hawking radiation. This process slowly drains energy from the black hole, causing it to evaporate over trillions of years. But if particles can escape as radiation, does the information they carry escape as well? Or is it forever lost? That is the heart of the information paradox. In recent decades, string theory, loop quantum gravity, and other advanced frameworks have all tried to describe what really happens at the edge of a black hole. Is it smooth? Is it violent? Is it a firewall, a region of high-energy particles incinerating anything that dares approach? Or is it an illusion, with all the drama happening only from the point of view of the outside observer? Even today, we don't have definitive answers. What happens at the event horizon may hold the key to a unified theory of physics, a bridge between the geometric elegance of Einstein's relativity and the probabilistic chaos of quantum mechanics. In many ways, the event horizon is the most extreme frontier in all of science. It represents the ultimate limit of observation. We cannot look beyond it. We cannot receive information from inside it. It is the cosmic curtain behind which nature keeps her deepest secrets. And yet, thanks to ingenious observation tools like the Event Horizon Telescope, we are finally beginning to catch glimpses of what this edge looks like from the outside. But as with any threshold in science, the closer we get, the more we realize how little we truly understand. The edge of the event horizon may not be the end of our knowledge, it may be the beginning of a new understanding of space, time, and information itself. Spaghettification. There is a term in astrophysics that sounds almost comical, even absurd. And yet, it describes one of the most terrifyingly real phenomena in the known universe, spaghettification. Don't let the name fool you, this is no culinary metaphor. Spaghettification is the grotesque stretching and compression of matter into long, thin strands as it falls into a black hole. It is not merely theory. It is the logical, mathematical consequence of the immense tidal forces near a black hole's event horizon. To understand this, let us imagine something, anything, approaching a black hole. It could be a star, a spacecraft, or even a human body. As it draws nearer to the black hole, the gravitational pull increases dramatically. But here's the key, that gravitational force doesn't increase uniformly. The part of the object closer to the black hole feels a stronger gravitational tug than the part farther away. This difference in gravitational pull is what we call a tidal force, and in the extreme environment near a black hole, it becomes devastating. Picture a person falling feet first toward a stellar mass black hole. The gravity acting on their feet is significantly stronger than the gravity acting on their head. As a result, their body is stretched vertically and compressed horizontally. The closer they fall, the more intense this difference becomes, until the individual is pulled into a long, narrow filament, thinner than a human hair, longer than a skyscraper. The atoms themselves may be torn apart. This is spaghettification. What's astonishing is how the scale of the black hole affects this phenomenon. For stellar mass black holes, which can be just a few kilometers across, spaghettification occurs outside the event horizon. This means you would be destroyed before even reaching the threshold of no return. But for supermassive black holes, millions or even billions of times more massive, the gravitational gradient at the event horizon is far gentler. In those cases, you could theoretically cross the event horizon without immediate damage, only to be torn apart deeper inside, closer to the singularity. So, paradoxically, the bigger the black hole, the safer the journey to the event horizon, though not the journey past it. Mathematically, these tidal forces can be derived directly from the equations of general relativity. The Riemann curvature tensor describes how spacetime bends, and when applied to a body falling into a black hole, it reveals the immense shearing forces at play. The closer one gets to the singularity, the more these curvature values diverge to infinity. Physically, that means that spacetime is no longer a smooth manifold, it becomes a violent, jagged chasm of infinite distortion. And no material object, no matter how strong or compact, can survive that. Some have speculated that, in extreme cases, even subatomic particles may not escape intact. The very wave function of a quantum particle may be stretched so much that it no longer retains a coherent identity. Information, once localized and structured, becomes diffuse and scattered. Whether this means information is lost is part of the infamous information paradox, a topic we'll explore in greater detail later. But in the context of spaghettification, it is clear, structure does not survive. Only the most basic components of matter might make it through, if anything at all. From a philosophical standpoint, spaghettification is a vivid illustration of the breakdown of classical intuition. In our daily lives, gravity is so weak that we think of it as a unifying force. It holds us to the Earth, keeps the planets in orbit, shapes the cosmos gently over eons. But near a black hole, gravity becomes alien. It doesn't unify, it annihilates. It shreds. It tears. The same force that built galaxies now becomes the engine of their destruction. Now, consider again the idea of observing someone falling into a black hole. From afar, we see them slow down, redshift fade. But to them, the journey continues. If the black hole is massive enough, they may not even feel the moment they cross the horizon. But eventually, regardless of size, they will reach the region where tidal forces become unmanageable. Their body, their ship, their atoms will be elongated along the radial direction of the black hole and compressed laterally until they are nothing but a string of particles plunging into the void. This brings us to a deeper, more unsettling idea. Is the singularity real? If we accept general relativity in its current form, then yes, the singularity is a real point of infinite density and zero volume. But if quantum mechanics is correct, then infinities should be banished from our physical theories. Some physicists believe that a theory of quantum gravity will eventually smear out the singularity, replacing it with a finite, though still extreme, region of curved spacetime. Until then, spaghettification remains our most visceral, most haunting vision of what awaits anything that dares venture too close to a black hole. Not a fiery death. Not an explosion. But an inescapable, silent, one-way journey into oblivion, drawn out and stretched until you are no longer recognizable as a structure, or even perhaps a particle. A final scream of existence reduced to a thin thread in the fabric of space and time. The strange beauty of it all is that this process, terrifying and inevitable, is not chaotic or unpredictable. It is written in the language of Einstein's equations. It is orderly, precise, and governed by the same mathematical truths that describe planetary orbits and falling apples. It is the universe doing exactly what the equations say it must. And perhaps that is what makes it most terrifying of all. Time dilation near the event horizon. Imagine standing at the edge of a vast, cosmic abyss. You look down, and there it is, the event horizon of a black hole, the very boundary where space and time begin to unravel. Now, imagine that your friend decides to take a brave, or perhaps foolish, leap and fall toward the black hole while you remain at a safe distance. What happens next isn't just strange. It's one of the most counterintuitive phenomena in all of physics: time dilation. To understand time dilation near the event horizon, we need to explore how gravity doesn't just pull on matter, it pulls on time itself. According to Einstein's general theory of relativity, gravity is not a force in the traditional sense. Instead, it's a curvature of spacetime caused by the presence of mass. The more massive an object is, the more it bends spacetime around it. Black holes are the ultimate expression of this phenomenon. They bend space-time so severely that not even light can escape their grip. Now, time is a dimension, just like space. As you move through space, you also move through time. But in the presence of a powerful gravitational field, time flows more slowly. This effect is known as gravitational time dilation, and it becomes extreme near a black hole's event horizon. Let's return to the scenario of your friend falling into the black hole. To them, time feels perfectly normal. Their wristwatch ticks, their heart beats, and their thoughts flow as usual. But to you, watching from a safe distance, something extraordinary happens. Their descent appears to slow down. As they approach the event horizon, their motion becomes sluggish, almost frozen. Their image becomes dimmer and redder, a result of gravitational redshift, until they fade completely. They never quite seem to cross the event horizon in your view. Time, for them, stretches infinitely from your perspective. This isn't an illusion. It's a real consequence of the way gravity warps spacetime. The coordinate time as measured by a distant observer, approaches infinity at the event horizon. So from your standpoint, your friend never quite falls in. They asymptotically approach the edge, getting closer and closer, slower and slower, redder and redder. But from your friend's perspective, the proper time experienced by the infalling observer, they cross the event horizon in finite time. Once inside, their journey continues toward the singularity in a matter of seconds or minutes. Two different experiences of time, both equally real, both fully valid within the context of general relativity. This paradox of time perception near a black hole gives rise to countless philosophical and physical questions. For example, does information about your friend remain forever suspended near the horizon, visible in theory but unreachable? Does the infinite time from your perspective mean they never quite disappear from the universe? Or is there some deeper truth hidden beneath this discrepancy? To dive deeper into the equations behind this, consider the Schwarzschild metric, the mathematical solution to Einstein's field equations for a non-rotating, uncharged black hole. It reveals that the rate at which time flows depends on your radial distance from the singularity. The closer you get to the event horizon, the Schwarzschild radius, the slower time becomes relative to a distant observer. Mathematically, the time dilation factor becomes infinite at the horizon itself. This isn't just theoretical. We've observed gravitational time dilation on Earth. GPS satellites orbiting above us must account for time flowing slightly faster than it does on the ground due to weaker gravity at higher altitudes. Without this correction, GPS systems would quickly become inaccurate. Now magnify that by billions. That's what's happening near a black hole. This dilation of time has profound implications. Suppose your friend had a way to hover just outside the event horizon without falling in, a near impossibility, but let's entertain the thought. From your viewpoint, their watch would tick slower and slower. Minutes would pass for them while centuries could pass for you. The black hole becomes a one-way time machine of sorts. A place where the future of the universe unfolds while you experience a brief moment. The closer you hover to the edge, the more extreme the time differential becomes. This concept forms the basis of many science fiction stories, where astronauts return from the edge of a black hole to find that thousands of years have passed on Earth. But it's not just fiction. It's grounded in the very fabric of our best physical theories. But there's more. Time dilation also affects light and information. As light tries to escape the gravity of the black hole, it loses energy, stretching into longer and longer wavelengths. This is gravitational redshift. Near the event horizon, the redshift becomes so extreme that the light is no longer detectable. It fades into nothingness. And so, the infalling object, your friend, fades not because they vanish, but because their emitted light is so stretched in time and wavelength that it becomes practically non-existent to outside observers. Some have proposed that this extreme dilation might allow a clever civilization to use the edges of black holes to observe the distant future of the cosmos. If you could hover just above the event horizon, again, a theoretical possibility with enormous energy requirements, you could, in principle, watch the entire future history of the universe unfold before your eyes in what would feel like mere seconds to you. Of course, doing so would come at an incredible cost. The radiation and tidal forces in such proximity would be extreme, and the engineering required to remain stationary near a black hole would defy current technological understanding. But the physics doesn't forbid it. Time dilation also plays a critical role in understanding the evaporation of black holes. From the perspective of an outside observer, Hawking radiation slowly causes the black hole to lose mass and shrink. Yet because time at the horizon is infinitely stretched, the final evaporation of the black hole takes an infinite amount of coordinate time. In other words, to an outside observer, the black hole never quite disappears. This further complicates the question of whether information is truly lost when something falls in. Even stranger are the implications when you factor in quantum mechanics. In quantum theory, processes are governed by probabilities, superpositions, and entanglements. But time dilation forces us to confront a scenario where quantum information is trapped in a region of space for a potentially infinite time, yet from another frame of reference, it has already passed into oblivion. Reconciling these perspectives is one of the most urgent challenges in modern physics. In this sense, the event horizon is not just a boundary in space, it's a boundary in time. It separates not just the inside from the outside, but two radically different experiences of reality. Two observers can disagree fundamentally about what happened and when, yet both are correct within the context of general relativity. And so, the event horizon becomes a mirror, not of light, but of time itself. It reflects the deep, mysterious nature of the universe, where cause and effect, past and future, here and there, are not as straightforward as they seem. Where one person's death plunge is another's eternal pause. Where time, the ever-flowing river of our experience, becomes fractured, bent, and ultimately unknowable. The firewall paradox. Just when we thought black holes couldn't get any weirder, nature throws us a curveball. The event horizon, once thought to be a smooth, uneventful boundary, may not be so calm after all. What if, instead of a quiet crossing, an infalling observer is instantly incinerated by a seething wall of high-energy particles? This is the question at the heart of one of the most unsettling and controversial ideas in modern theoretical physics, the firewall paradox. To appreciate the strange and almost heretical nature of the firewall hypothesis, we need to revisit three foundational pillars of physics. First, quantum mechanics, which tells us that information can never be destroyed. Second, general relativity, which tells us that an infalling observer should experience nothing unusual at the event horizon, a principle known as the equivalence principle. And third, black hole thermodynamics, where Hawking radiation appears to slowly leak energy, and possibly information, away from the black hole. Here's where the trouble begins. When Stephen Hawking proposed that black holes emit radiation, it raised a thorny issue. This Hawking radiation is thermal. It looks completely random. If you throw something into a black hole, the information about it seems to disappear, because the Hawking radiation coming out contains no trace of what fell in. This is the infamous black hole information paradox. Quantum mechanics says information must be conserved, but Hawking radiation appears to erase it. For decades, physicists tried to resolve this conundrum. Could information somehow be stored at the event horizon? Could it escape with Hawking radiation in subtle ways we don't yet understand? Could it survive in a remnant of the black hole after evaporation? Then came a radical proposal in 2012 from physicists Ahmed Amhiri, Donald Maroff, Joseph Polchinski, and James Sully, collectively known as AMPS. They suggested that if you accept the unitarity of quantum mechanics, that information is never lost, and you accept the validity of Hawking radiation, then the smoothness of the event horizon, the no drama assumption from general relativity, must be wrong. Instead of gently falling through the horizon, any infalling observer would encounter a wall of fire, a barrier of searing, energetic particles that burns them to ash. This firewall violates everything we thought we knew about black holes. The equivalence principle, a cornerstone of general relativity, says that a falling astronaut should feel nothing as they cross the event horizon. In fact, for a supermassive black hole, the tidal forces at the horizon would be negligible. It should be like floating in space. But the firewall idea says, no. There's a discontinuity, a violent transition, where nothing should exist. So why does this paradox arise? It comes down to entanglement. In quantum mechanics, particles can be entangled. They share information in such a way that measuring one instantly affects the state of the other, no matter how far apart they are. Hawking radiation, according to theory, involves pairs of entangled particles. One falls in, the other escapes. Over time, the escaping particles become entangled with the ones that previously escaped. But there's a problem. Quantum theory forbids monogamy of entanglement. A particle can't be maximally entangled with two other particles at the same time. But in this case, each new escaping particle would need to be entangled both with its partner that fell into the black hole, and with earlier Hawking radiation that has already escaped. That's not allowed. Something has to give. So AMPS proposed that the only way out is to break the entanglement between the inside and the outside. But breaking entanglement has consequences. It leads to a surge of high-energy particles at the horizon, a firewall. This idea was met with shock. If true, it would mean that general relativity fails at the event horizon. That black holes are not the smooth, gentle wells of spacetime we once imagined, but instead host one of the most violent environments in the universe, an invisible curtain of annihilation. Yet not everyone agrees. Many physicists believe the firewall paradox is telling us something deeper, that our understanding of spacetime, gravity, and quantum information is incomplete. Maybe there's a new principle waiting to be discovered, one that resolves the paradox without requiring firewalls. Perhaps it lies in the domain of quantum gravity, a theory that doesn't yet fully exist. One proposed solution involves the ER equals EPR conjecture, put forth by Leonard Susskind and Juan Maldacena. This idea suggests that entangled particles, EPR pairs, are connected by tiny wormholes, Einstein-Rosen bridges. In this view, the entanglement between Hawking radiation and the black hole interior could be described geometrically, not just quantum mechanically. If true, this might allow information to escape the black hole without violating entanglement rules or invoking a firewall. Others turn to the AD/CFT correspondence, a theory in string theory that equates a gravity theory in higher dimensions with a quantum field theory on its boundary. This duality has helped physicists model black hole behavior in simpler terms, but so far, it hasn't fully resolved the firewall debate. Then there's the fuzzball proposal from string theory, which we'll discuss more deeply later. This model replaces the event horizon with a tangled mass of strings, a fuzzball, with no clear inside or outside. In this case, there's no need for a firewall, because there's no traditional horizon for anything to cross. Still, the firewall paradox hangs like a dark cloud over black hole physics. It forces us to confront uncomfortable questions. Is the equivalence principle always true? Can quantum mechanics and general relativity really be unified? Are event horizons smooth, or are they the most brutal boundaries in nature? It also raises observational challenges. If firewalls exist, can we detect them? Current observations of black holes, including those from the Event Horizon Telescope, reveal no sign of such violent boundaries. But we're only seeing shadows and accretion disks, not the event horizon itself. The true nature of the horizon remains hidden behind an opaque curtain of theory. The firewall paradox may not be a literal wall of fire. It might be a metaphor for something deeper, a breakdown in our current understanding. A signal that the union of quantum mechanics and gravity demands a new kind of thinking. A signal that the fabric of reality, like the horizon itself, may not be what it seems. And perhaps the most chilling implication of all, if firewalls are real, then the dream of a smooth journey into the cosmic abyss may be dead. Instead of slipping quietly into the black hole's core, future explorers might meet their end not at the singularity, but at the very edge, where space, time, and everything we know bursts into flames. Information paradox and quantum entanglement. In the vast intellectual landscape of theoretical physics, few debates have generated as much controversy, obsession, and innovative thinking as the black hole information paradox. This enigma strikes at the very heart of how the universe works, where gravity, quantum mechanics, and information theory collide in a singular explosion of uncertainty. At its core, the information paradox asks a deceptively simple question: what happens to information that falls into a black hole? To unpack this, let's revisit a fundamental principle of quantum mechanics: unitarity. Unitarity asserts that the evolution of quantum systems preserves information. If you know the quantum state of a system at one moment in time, you can, in principle, determine its state at any earlier or later time. Information is never lost. It can be scrambled, entangled, diffused, or hidden, but never destroyed. Now, let's imagine dropping an encyclopedia into a black hole. According to general relativity, the book would fall past the event horizon, eventually reaching the singularity at the core. Once past the event horizon, no signals can escape. The information in that encyclopedia, its words, paper, and ink molecules, disappears from the observable universe. Stephen Hawking's seminal work in the 1970s made this even more troubling. He showed that black holes radiate particles through a quantum process now called Hawking radiation. These particles are completely thermal. They appear to carry no information. Over unimaginable stretches of time, this radiation slowly drains the black hole of its mass, eventually causing it to evaporate and vanish. So here's the problem. If black holes evaporate into nothing but thermal radiation, and that radiation carries no record of what fell in, then information has been destroyed. And that is a direct violation of quantum mechanics. This contradiction between Hawking's black hole radiation and the laws of quantum theory is the information paradox. Either information is lost, and quantum theory is incomplete, or our understanding of black holes is fundamentally flawed. To add more depth to this already tangled mess, let's bring in the concept of quantum entanglement. In Hawking's original picture, Hawking radiation forms when pairs of virtual particles pop into existence just outside the event horizon. One particle escapes into space, while its partner falls into the black hole. These two particles are quantum entangled. Their states are linked in such a way that measuring one instantaneously affects the state of the other, even across vast distances. Now, consider what happens over time as more and more Hawking radiation escapes. If the early emitted particles are entangled with their partners inside the black hole, and the later emitted particles are also entangled with their own infalling partners, then something strange happens. The radiation outside the black hole becomes more and more entangled with what's inside. But as the black hole shrinks, there's less and less of it left to be entangled with. Eventually, this leads to a situation where the radiation outside appears to be entangled with more than one thing, which quantum mechanics strictly forbids. This is the monogamy of entanglement problem. One quantum system cannot be maximally entangled with two separate systems. It's like trying to have a best friend who is also someone else's best friend in an exclusive game. It just doesn't work. This breakdown suggests that either Hawking's calculation is wrong, or our understanding of entanglement in curved spacetime is incomplete. Resolving this conflict is one of the deepest unsolved challenges in modern physics. A variety of proposals have been made to resolve the paradox. One idea suggests that information is encoded in subtle correlations between Hawking radiation particles. The radiation might appear random, but hidden within it are complex patterns that, over time, allow information to leak out of the black hole, a process known as information recovery. If true, the final stages of evaporation would release all the information that had fallen in. This would mean Hawking radiation is not purely thermal, it contains quantum correlations. However, calculating these correlations is incredibly difficult, and we lack the observational power to test this directly. Another theory posits that information is stored at the event horizon itself, possibly as a holographic projection. This leads us to the idea of black hole complementarity, which we'll explore later. In this framework, different observers, one falling into the black hole and one remaining outside, see different versions of reality. But no paradox arises because no single observer sees a contradiction. Then there's the fuzzball theory from string theory, which replaces the traditional black hole with a tangle of vibrating strings. In this picture, there is no event horizon as we usually conceive it. Information doesn't disappear behind a veil. Instead, it's smeared out across the fuzzball's surface, and radiation carries it away in a non-thermal, information-rich form. Still, these ideas face strong theoretical and empirical challenges. Some physicists have taken a different approach entirely, using the mathematical tools of quantum information theory. The Page curve, named after physicist Don Page, describes how the entropy of Hawking radiation should evolve if information is preserved. According to this curve, entropy initially increases as radiation accumulates, but then decreases in the later stages of evaporation, implying that radiation becomes more ordered and information-rich over time. For decades, Hawking radiation did not fit the Page curve. But recent work using tools from the ADS/CFT correspondence, which equates gravitational systems with quantum field theories, has shown that it is possible to reproduce the Page curve in certain models. These calculations have given physicists new hope that black holes may indeed preserve information after all. Another tantalizing concept is ER equals EPR, the bold conjecture that wormholes, Einstein-Rosen bridges, or ER, and quantum entanglement, Einstein-Podolsky-Rosen pairs, or EPR, are actually the same thing. In this framework, entangled particles are connected through tiny, non-traversable wormholes. If correct, this could mean that the black hole interior is connected to its emitted Hawking radiation via quantum bridges. In this strange geometry, information could travel through spacetime without violating causality or quantum theory. And what about experimental verification? Can we ever test these ideas? Probably not directly. The physics of event horizons and entanglement is currently beyond the reach of terrestrial experiments. Black holes are distant, opaque, and hostile. Their radiation is too faint to detect, and their interiors are forever out of reach, at least according to classical physics. However, there is hope in the form of simulated black holes and quantum analog systems, where event horizon-like conditions are created in laboratory settings using fluids, Bose-Einstein condensates, and photonic crystals. Some of these systems even show behavior reminiscent of Hawking radiation and entanglement. In these tabletop experiments, we might glimpse the underlying principles of black hole thermodynamics and information recovery, offering hints about the deeper fabric of reality. The information paradox and the role of quantum entanglement continue to force physicists to rethink everything we thought we knew. It is not just a question of black holes, it is a question of whether the universe preserves its own history. Whether the story of every atom, every photon, every collapsed star and particle accelerator will someday be written again, or lost forever to the void. It's a cosmic whodunit, a metaphysical mystery, and perhaps the ultimate key to unifying the laws that govern our cosmos. Hawking radiation and black hole evaporation. In the cold silence of space, where time stretches and matter collapses, one of the most astonishing discoveries of the 20th century emerged not from a telescope but from the mathematical imagination of Stephen Hawking. It was a revelation that shook the very foundations of physics, a realization that black holes, those cosmic abysses thought to be eternal, might not be eternal after all. They could radiate. They could evaporate. They could die. This phenomenon, now known as Hawking radiation, blurs the line between the quantum and the gravitational, between the vacuum and the void, and has implications that reach into the deepest recesses of the universe. But how does a black hole, whose very name implies a one-way trap for matter and light, emit anything at all? To understand Hawking radiation, we must first look at the quantum vacuum. Contrary to popular belief, the vacuum of space is not truly empty. It teems with invisible activity. At the smallest scales, governed by the rules of quantum field theory, energy fluctuations continuously give rise to virtual particle pairs, a particle and its corresponding antiparticle, that blink into existence for infinitesimal moments before annihilating each other. Now imagine such a pair forming near the event horizon of a black hole. Normally, the pair would vanish back into the vacuum as quickly as it appeared. But if one particle falls into the black hole while the other escapes, the annihilation cannot occur. The escaping particle becomes real, observable energy, Hawking radiation. From an outside perspective, it appears as though the black hole is emitting particles. But where does the energy for this radiation come from? The answer lies in the black hole itself. the particle that falls and carries negative energy relative to the outside universe. As it crosses the event horizon, it effectively reduces the mass of the black hole. Over time, with countless virtual pairs separating this way, the black hole gradually loses mass. This process is slow, extremely slow, for stellar mass black holes, but it becomes more significant for smaller black holes. Eventually, in a process that could take trillions upon trillions of years, the black hole loses all of its mass and evaporates completely, ending in a final burst of radiation, possibly releasing enormous energy in a brief moment, depending on the nature of the singularity. Let's be precise. Hawking's calculation showed that black holes radiate like black bodies, objects that emit a spectrum of thermal radiation. The temperature of this radiation is inversely proportional to the black hole's mass. Large black holes are extremely cold, radiating so faintly that the cosmic microwave background outshines them. But as they shrink, they grow hotter. A black hole the size of a mountain, for instance, would radiate significant energy, and a black hole with the mass of a spaceship would be white hot. This has led to fascinating speculation about miniature black holes, possibly created in the early universe or even, in theory, inside high-energy particle colliders like the LHC. These tiny black holes would evaporate much faster and might already be gone if they ever existed. But this also introduces some mysteries. As a black hole evaporates, what happens to the information it contains? As discussed in the previous segment, if Hawking radiation is truly random and carries no memory of what fell in, then information seems to be permanently lost, a violation of the core tenets of quantum theory. This is the seed of the black hole information paradox. If a black hole disappears completely and all it leaves behind is thermal radiation with no structure, we face a contradiction. Either general relativity is wrong in some way, or quantum mechanics is incomplete. Hawking himself wrestled with this question for decades. Initially, he believed information was lost. Later in his life, he revised his stance, suggesting that perhaps information is preserved through subtle quantum effects at the event horizon or through holographic principles. But the full answer remains elusive. To add to the intrigue, Hawking radiation is not just a theoretical curiosity. It connects deeply to black hole thermodynamics, a framework that suggests black holes obey laws remarkably similar to those of heat and energy. In this view, the surface area of the event horizon corresponds to entropy, a measure of disorder or information content. As the black hole radiates, its entropy decreases, and its temperature rises, again, like a black body. This is incredibly profound, suggesting that a black hole is not a simple void, but a complex thermodynamic object with a well-defined internal state. Let's consider the numbers. A black hole with the mass of the Sun has a temperature of about 60 nanokelvins, far colder than the cosmic microwave background. That means it would absorb more radiation from the universe than it emits, causing it to grow rather than shrink. Only when the universe becomes colder than the black hole can evaporation begin in earnest. Thus, Hawking radiation isn't just about shrinking black holes. It's about the destiny of matter and energy, the death of stars, and the fate of the universe itself. In a far future, trillions of years hence, after the last stars have faded and the galaxies have dimmed, black holes may be the final bastions of mass. And even they will not last. Slowly, silently, they will leak their substance into space, vanishing into a whisper of quantum particles. The last glow of existence. Some models predict that when a black hole shrinks to the Planck-scale, the smallest meaningful unit of length, it might cease to evaporate, leaving behind a black hole remnant. Others suggest that the final burst could release all the information trapped inside in a flash of energy. Still others propose that the end of evaporation might lead to the creation of a white hole, a hypothetical mirror image of a black hole that ejects matter rather than consuming it. These ideas remain speculative, but they show how Hawking radiation opens the door to new realms of cosmological thinking. But how do we observe Hawking radiation? Sadly, we don't, at least not yet. Its faintness, especially for large black holes, makes it essentially undetectable by current instruments. The best hope for detection lies in observing primordial black holes, tiny remnants from the Big Bang that may be evaporating now, releasing detectable bursts of gamma rays. Searches are ongoing, but no definitive evidence has been found. Alternatively, as mentioned earlier, laboratory analogues of Hawking radiation have been created. In these systems, ranging from fluid dynamics to ultracold atoms, researchers have simulated horizons and observed thermal emissions, offering indirect confirmation of the principles behind Hawking's theory. What Hawking radiation gives us is not just a mechanism of decay, but a philosophical shift. It tells us that no structure, no star, no singularity is eternal. Even the mightiest forces of gravity must bow to the laws of quantum physics. Even the most extreme objects in the cosmos are part of the universal cycle of creation, transformation, and decay. And it reveals something else, that black holes are not monsters, but messengers. That in their deaths, they speak to us across space and time, whispering secrets of the universe's deepest laws. The no-hair theorem. In the unfathomable depth of space-time where matter is crushed, time is twisted, and the ordinary laws of physics tremble, black holes rise as enigmatic singularities, simplified by their extremity, yet rich in mystery. Among the most curious aspects of their nature is something both elegant and unsettling, the no-hair theorem. This concept, as simple as it sounds, tells us that black holes are shockingly minimalistic. According to the no-hair theorem, once an object collapses into a black hole, all information about the object is lost, except for three fundamental properties: mass, electric charge, and angular momentum, spin. To put it bluntly, you could throw a library of books, a diamond-encrusted planet, or an entire alien civilization into a black hole, and once it crosses the event horizon, the black hole doesn't care. All that emerges on the outside is the black hole's mass, charge, and spin. Everything else, the object's composition, structure, and even identity, is erased from the observable universe. But why no hair? The phrase was first coined by physicist John Archibald Wheeler, who colorfully summarized this idea by saying, "Black holes have no hair." The term, hair, here refers to any additional observable information or distinguishing characteristics. Just as hair can be styled, colored, or shaped to define personality, hair, in physics would mean unique features of matter before it fell in. According to this theorem, black holes are bald. They have no distinguishable traits beyond those three parameters. Let's examine those three remaining attributes. 1. Mass. This is the simplest and most intuitive. The mass of the black hole determines the strength of its gravitational pull and the size of its event horizon. More mass means a larger and stronger black hole. 2. Electric charge. Though most astrophysical black holes are expected to be electrically neutral, since they would attract opposite charges and neutralize themselves, the theory allows for charged black holes, described by the Reissner-Nordström solution. 3. Angular momentum. This is the black hole's spin. When a star collapses, any rotation it has is conserved, causing the resulting black hole to spin. Rotating black holes are described by the Kerr solution, and their rotation has profound implications, including frame-dragging effects and the possibility of energy extraction via the Penrose process. When a black hole settles into a stable state, its gravitational field outside the event horizon is completely determined by just these three parameters. This is what makes the no-hair theorem so strange. It implies that two black holes of the same mass, charge, and spin are indistinguishable, no matter how differently they were formed. But the implications go deeper, into the very core of physics. This concept conflicts with our understanding of quantum mechanics, where information is never truly lost. The unitarity of quantum mechanics demands that the evolution of a system's wave function is deterministic and reversible. If black holes erase all information except for mass, charge, and spin, it would violate this principle. Hence, the no-hair theorem is one of the key pillars leading to the black hole information paradox. Now consider this: if black holes erase identity, what does that mean for entropy? How can we define entropy if we can't know the internal microstates of a black hole? Enter Jacob Bekenstein, who proposed that black holes do have entropy and that it is proportional to the area of the event horizon, not the volume. This was a revolutionary idea. It suggested that the information about what fell and might be encoded on the surface of the black hole. This concept later evolved into the holographic principle, which we'll discuss more deeply in upcoming segments. But the no-hair theorem still stands strong in classical general relativity. Solutions to Einstein's field equations, such as the Kerr-Newman metric, reinforce the idea that a black hole is fully described by only three quantities. However, things become more complicated when we bring in quantum field theory, string theory, or other attempts at quantum gravity. Some physicists argue that black holes do have hair, but it's soft hair, subtle quantum effects that may carry the imprints of the information lost. These ideas are still being developed, but they represent a direct challenge to the classical interpretation of the theorem. There are also exceptions to the no-hair theorem. In non-Einsteinian models of gravity, such as scalar tensor theories, higher-dimensional spacetimes, and string theory-inspired models, black holes can support additional fields or hair. These exotic models suggest that the black holes we see in our universe may not be the whole story. Experimental verification of the no-hair theorem is a major goal of gravitational wave astronomy. When two black holes merge, the final remnant settles down, emitting gravitational waves known as the ring-down phase. The frequencies of these waves depend only on the mass and spin of the final black hole. If we detect deviations from this prediction, it might imply the existence of hair, additional structure that challenges general relativity. This is why observatories like LIGO and Virgo are so crucial. Each merger event brings us closer to testing whether the universe is as bald as the theorem suggests. Furthermore, the Event Horizon Telescope has offered us images of the shadow of a black hole, and though it's not yet fine-grained enough to probe hair directly, future improvements could help confirm whether the spacetime geometry truly matches the predictions of hairless models. So where do we stand? The no-hair theorem tells us that black holes are simple in a cosmic sense, but that simplicity hides deep questions. If information is lost, it challenges quantum theory. If information is preserved, we must explain how it's encoded and where it hides. Do black holes have hair? Are they as featureless as the theory suggests? Or is their baldness an illusion created by our limited understanding? Perhaps, in the quantum realm where spacetime trembles and particles dance on the edge of uncertainty, the black hole holds secrets in folds too subtle for our current theories to grasp. Perhaps the hair is there, hidden in vibrations of the event horizon, in quantum foam, or in microscopic strings coiled in the shadows. And maybe, just maybe, the next great discovery in physics will come not from what black holes erase, but from what they remember. Observer versus infalling experience. As we journey further into the mind-bending landscape surrounding black holes, a new mystery presents itself, one that cuts to the very heart of perception and reality. The stark difference between what a distant observer sees and what an infalling traveler experiences near a black hole's event horizon. This difference isn't just a trick of perspective. It is a fundamental result of Einstein's general theory of relativity, and it forces us to confront the idea that reality might not be the same for everyone. Let us step into this paradoxical world where truth becomes relative. Imagine a brave astronaut floating near a black hole. For them, time ticks normally. They check their watch, tap their helmet, and proceed on their mission. If they begin to fall inward toward the event horizon, from their point of view, everything feels eerily smooth. No alarms sound. No invisible wall stops them. As they pass the event horizon, they notice nothing special. It's just empty space. But behind them, the universe begins to vanish. Light from distant stars grows redder and dimmer. The past becomes unreachable, the outside world lost. But now imagine a distant observer, say, a scientist watching the same astronaut through a telescope from a safe distance. What they see is completely different. To them, the astronaut slows down as they approach the event horizon, creeping ever more sluggishly toward it. The closer the astronaut gets, the slower they appear to move. Their clock ticks more slowly. Their voice becomes stretched and distorted. Their image dims and reddens due to gravitational redshift until it eventually fades into invisibility, hovering like a ghost just above the event horizon, frozen in time. This stunning divergence of experiences is not a mathematical oddity, it's a real consequence of how space-time behaves near a black hole. From the infalling astronaut's perspective, time moves as usual. But from the perspective of the distant observer, time for the astronaut effectively stops as they approach the horizon. Let's break this down. Time dilation is the effect where time passes at different rates depending on gravity and motion. The stronger the gravitational field, the slower time flows relative to a region with weaker gravity. Near the event horizon of a black hole, space-time is warped to such a degree that this difference becomes extreme. For the distant observer, the astronaut's time slows to an infinite crawl. This phenomenon can be explained using the Schwarzschild metric, the solution to Einstein's field equations for a non-rotating, uncharged black hole. The equations predict that at the event horizon, the gravitational time dilation becomes infinite. To an outside viewer, the infalling object never actually reaches the event horizon in finite time. Instead, it appears to freeze and fade. But for the infaller, the journey continues unimpeded. Once inside the event horizon, all paths lead inward toward the singularity. There is no turning back, no possibility of sending messages home. The event horizon acts like a one-way membrane, allowing passage only inward. Light emitted from within the event horizon cannot escape. It's as though the speed of light is simply not fast enough to overcome the gravity. Now, consider the question, which observer is right? The answer is unsettling. Both are correct, in their own reference frames. This duality challenges our idea of an objective, universal reality. It shows that what is real in the universe can depend on the observer. In some sense, both experiences exist simultaneously, the astronaut falling inward and seeing nothing unusual, and the observer seeing the astronaut frozen at the edge of oblivion. This dual perspective leads to deep philosophical and physical questions. For instance, if the astronaut carries information, say, a notebook filled with equations or a sample of alien DNA, what happens to that information? From the distant observer's view, the astronaut never quite enters the black hole. So does the information remain encoded in the faint radiation near the horizon? Or does it plunge inward and get crushed at the singularity? This feeds directly into the black hole information paradox, a crisis in theoretical physics that pits quantum mechanics against general relativity. Furthermore, the discrepancy between observer and infaller is central to ideas like black hole complementarity, which proposes that no single observer can witness violations of physical laws. In other words, an infalling observer might see one version of events, and a distant observer another, but neither can compare notes. The laws of physics remain intact in each observer's world, as long as their experiences remain fundamentally unshareable. This idea also plays a pivotal role in discussions of the firewall paradox, which we'll explore soon. The firewall hypothesis posits that an infalling observer might be incinerated at the event horizon by high-energy quanta, a result that contradicts general relativity's prediction of a smooth, featureless fall. But from a distant observer's standpoint, the astronaut never quite reaches the firewall. Again, two realities coexist, yet cannot contradict one another. Moreover, this observer-infalling split is not just theoretical. It echoes through our understanding of causality and information flow in the universe. It makes us question what it means to see an event and whether observations define reality. Does an event truly happen if it cannot be observed? Is the event horizon a place, or is it simply a boundary that depends on your point of view? Some researchers believe that these questions hint at a deeper, perhaps more radical truth about the universe. It may be that space-time itself is not fundamental, but emergent, that it arises from deeper quantum information processes. In that view, the differences between observers are features of a larger, more profound structure of reality, one we have yet to fully grasp. For now, the observer versus infalling paradox remains one of the most intriguing aspects of black hole physics. It reminds us that reality is not always as it seems, and that our place in the universe, our vantage point, shapes what we perceive as true. Perhaps one day, a more complete theory of quantum gravity will reconcile these perspectives. Until then, we must accept the duality of the black hole's edge, a place where time stands still, and yet everything falls through. Virtual particles and the quantum foam. As we continue our voyage along the edge of one of the universe's most mysterious structures, the event horizon of a black hole, we now take a microscopic detour. This detour doesn't involve planets or stars or galaxies. Instead, we shrink ourselves down to a scale so infinitesimally small that space-time itself becomes turbulent, frothy, and unpredictable. Welcome to the realm of virtual particles and quantum foam, where the vacuum is not empty and the very structure of reality flickers with activity. To understand what happens at the boundary of a black hole, we must first recognize a startling truth: even what we think of as empty space is not truly empty. In the strange world of quantum field theory, the vacuum is a bubbling cauldron of energy and fluctuation. At any given moment, pairs of particles and antiparticles are continuously blinking into and out of existence. These are called virtual particles, and although they can't be directly observed, their presence has measurable effects. This restless activity is a product of Heisenberg's uncertainty principle, which states that certain pairs of physical properties, like energy and time, cannot both be known with perfect precision. If you allow a violation of energy conservation for a short enough time, so short that the uncertainty principle allows it, then nature permits the temporary appearance of particle pairs. These virtual particles exist for a fleeting moment before annihilating one another and returning their borrowed energy to the vacuum. But something extraordinary happens near an event horizon. When a virtual particle pair appears near the event horizon of a black hole, there's a chance that one of the particles will fall past the point of no return, while the other escapes into space. When this occurs, the escaping particle becomes real. It's no longer virtual. It can be detected, measured, and astonishingly, contributes to what we call Hawking radiation. The particle that escapes effectively steals energy from the black hole, while its doomed twin plunges inward with negative energy relative to the outside world. This leads to a slow decrease in the black hole's mass, an evaporation that, over immense timescales, can cause the black hole to vanish entirely. We'll return to this phenomenon in depth when we explore Hawking radiation, but for now, it's crucial to recognize that this escape mechanism is rooted in the physics of virtual particles near the event horizon. But what is the medium through which these virtual particles dance? That brings us to the concept of quantum foam, a term coined by physicist John Wheeler to describe the idea that at the Planck-scale, space-time is not smooth, but chaotic and fluctuating. On scales of about 10 to the power of -35 meters, the very geometry of space becomes uncertain. Tiny wormholes may open and close. Loops of space-time might form and evaporate. The energy density of the vacuum is so high, and the timescales so brief, that space-time cannot remain calm. It seethes with randomness. Picture a churning sea, but replace the water molecules with microscopic fluctuations in the shape and fabric of space itself. Black holes, and especially their event horizons, are where the macro scale meets the microscale. These are the natural laboratories for exploring the wild terrain of quantum gravity, a theory that would unite Einstein's general relativity with quantum mechanics. In classical general relativity, the event horizon is a crisp, clean boundary. But when quantum mechanics is taken into account, the edge begins to blur. It becomes a dynamic interface between the smooth, continuous field of spacetime and the jittery, probabilistic world of particles and fields. Some theories propose that the event horizon is not a surface at all, but a kind of phase transition, like the boundary between water and steam. Others suggest that it is a quantum boundary, made up of entangled bits of information encoded on its surface. We'll explore these radical possibilities further when we examine the notion of holographic event horizons, but for now, it's enough to realize that virtual particles and quantum foam are not just theoretical curiosities. They may be key to understanding how black holes form, evolve, and ultimately fade away. An intriguing question arises: could the black hole's entire interior be replaced by quantum foam? This leads to proposals like the fuzzball model, which suggests that instead of a singularity inside a smooth event horizon, a black hole is made up of a complex tangle of strings or brains from string theory. In this model, the classical idea of a smooth interior collapses under the weight of quantum complexity. Even more radically, some physicists speculate that black holes themselves may be illusory, mere mirages created by the quantum behavior of spacetime and fields. In such views, the distinctions between inside and outside might not even exist at the most fundamental level. Virtual particles, quantum foam, and entanglement would become the fabric from which reality itself is woven. This brings us to one of the deepest implications of all. If space and time are composed of fluctuating, entangled, ephemeral components, then what we call reality is not a solid foundation, but a shifting network of probabilities and interactions. Black holes, as boundaries where quantum foam and curved spacetime meet, represent our best chance to understand this deeper structure. And while we are far from a complete theory of quantum gravity, virtual particles offer a tantalizing hint. They suggest that the void is not empty, and that the boundary of a black hole is not just a line drawn in spacetime, but a gateway into the quantum depths of reality. So, the next time we imagine the abyss at the edge of a black hole, we should not think of it as a simple boundary or a silent wall. Instead, we should picture a vibrant, chaotic, shimmering interface, a region buzzing with spontaneous creations and annihilations, a place where spacetime quivers under the pressure of uncertainty, and the universe itself begins to whisper the secrets of its quantum soul. Einstein's equations versus quantum mechanics. As we peer deeper into the theoretical underpinnings of black holes and event horizons, we arrive at one of the most fundamental conflicts in all of physics, one that has resisted resolution for over a century. This is not merely a disagreement over data or observation. It is a war of worldviews, fought between two pillars of modern science: Einstein's general relativity and quantum mechanics. General relativity, Einstein's magnum opus, is a classical theory of gravity. It describes spacetime as a smooth, four-dimensional continuum that curves in response to the presence of mass and energy. This curvature tells matter how to move, and matter tells spacetime how to curve. It is elegant, deterministic, and continuous. When we apply general relativity to black holes, we get precise predictions for how they warp space, how light behaves near them, and how the event horizon forms a boundary from which no classical information can escape. On the other hand, quantum mechanics is probabilistic, discrete, and grounded in uncertainty. It governs the behavior of the tiniest particles, electrons, photons, and quarks, and is fundamentally rooted in non-determinism. Particles do not have precise positions and velocities. Instead, they exist in superpositions, governed by wave functions that evolve over time. Observation collapses this wave function into a particular outcome. These two frameworks both work exceedingly well in their respective domains. Relativity reigns over the cosmic, the massive, and the slow-moving. Quantum theory rules the microscopic, the energetic, and the fast-moving. But when we try to apply both theories simultaneously, as we must do near the event horizon of a black hole, or inside it, the mathematics breaks down. Predictions become inconsistent. Infinities emerge where none should exist. Our equations, once precise and elegant, begin to sputter like a broken engine. Nowhere is this conflict more apparent than at the singularity, the mathematical point inside a black hole where density becomes infinite and the curvature of spacetime becomes undefined. General relativity tells us that this singularity exists, and that it lies at the heart of every black hole. But quantum mechanics balks at this conclusion. Infinite densities and zero volume points are incompatible with the uncertainty principle. Something must give. Attempts to unify these theories into a single framework, one that can describe both gravity and quantum phenomena, have led to the pursuit of quantum gravity, a theory that remains elusive to this day. Various approaches have been proposed, each offering different insights into the nature of spacetime, black holes, and the event horizon itself. One of the most promising candidates is string theory, which replaces point particles with tiny, vibrating strings of energy. In this framework, black holes may be composed of tangled strings, and the event horizon may be a dynamic, fluctuating membrane. String theory also suggests the existence of additional dimensions beyond the familiar four, dimensions that might be compactified or hidden, but which play a role in shaping the universe's geometry. Another approach is loop quantum gravity, which posits that space itself is quantized, made up of discrete chunks woven together like a fabric. In this model, the smooth space-time of general relativity emerges from a deeper quantum structure. Black holes, instead of having singularities, might contain quantum bridges or bounces, possibly connecting to other regions of the universe, or even to other universes. At the heart of the tension is a simple question: how do we reconcile the smooth, geometric world of Einstein with the grainy, probabilistic world of quantum physics? One is a theory of fields and curvature. The other is a theory of wave functions and operators. Yet both are correct in their own realms. Nowhere is this contradiction more pronounced than at the event horizon. According to general relativity, nothing, no information, no light, no particles, can escape from within this boundary. Once crossed, the fate of any object is sealed. But quantum mechanics has a different story. According to quantum field theory in curved spacetime, black holes can radiate particles, a process known as Hawking radiation. This radiation carries away mass and energy, and possibly information. The event horizon, once thought to be an absolute boundary, begins to look more like a semi-permeable membrane. This leads to deep philosophical questions. If black holes can evaporate over time, what happens to the information that fell into them? Is it truly lost forever, violating the principle of unitarity in quantum mechanics? Or is it somehow encoded in the radiation, perhaps through entangled states or quantum correlations? This is the infamous information paradox, and it cuts to the core of both theories. Einstein's equations offer no mechanism for preserving quantum information. They are classical, deterministic, and blind to the intricacies of the quantum world. But quantum mechanics insists that information cannot be destroyed. Every interaction, every process, every evolution must, in principle, be reversible. Resolving this paradox requires more than just clever mathematics. It demands a revolution in our understanding of space, time, and reality itself. Some physicists propose that the event horizon is not a smooth, featureless boundary, but a holographic surface where every bit of information about the interior is encoded. Others suggest that information may be scrambled but preserved, hidden in correlations so subtle that they elude detection. Still others argue for more radical possibilities, that black holes are not real objects, but emergent phenomena, that spacetime itself is a projection from a deeper, non-spatial realm, or that our very notions of causality and locality must be rewritten. At the center of this storm lies the event horizon, simultaneously a physical boundary and a philosophical battleground. It is where Einstein's legacy collides with the quantum revolution, and where our most cherished assumptions about the universe begin to unravel. Yet the stakes are higher than academic pride or theoretical consistency. The resolution of this conflict could unlock the secrets of the early universe, shed light on the true nature of time, and reveal whether the cosmos is a simulation, a computation, or something stranger still. For now, we stand at the edge, looking into the abyss. The equations on the chalkboard shimmer with mystery. The simulations strain against the limits of our supercomputers. And the black hole, silent and stoic, holds its secrets close. What lies beyond the event horizon is not just a question of astrophysics. It is a question of existence itself. Could the event horizon be a hologram? The deeper we dive into the enigmatic depths of black holes, the more we are confronted with theories that stretch the very fabric of reality. One of the most provocative of these is the holographic principle, an idea that challenges our understanding of space, information, and dimensions themselves. Could it be that everything that happens inside a black hole, everything swallowed by the event horizon, is somehow encoded on its surface? Could the boundary itself be a hologram of the entire interior? This idea didn't come from science fiction. It emerged as a serious proposition from the fertile minds of theoretical physicists like Gerard T. Hooft and Leonard Susskind, and it gained traction in the 1990s due to developments in string theory and quantum gravity. The holographic principle proposes something astonishing. All the information contained in a volume of space can be described by data encoded on its boundary. Just like a hologram, a two-dimensional surface that creates a three-dimensional image, our three-dimensional universe, or at least certain aspects of it, may be a projection of information written on a two-dimensional surface. To understand how this relates to black holes, we need to revisit the Bekenstein-Hawking entropy. Jacob Bekenstein proposed that black holes possess entropy, a measure of information or disorder, and that this entropy is proportional not to the volume of the black hole, but to the area of its event horizon. This was counterintuitive. In ordinary systems, entropy scales with volume. But for black holes, it's the surface that matters. Stephen Hawking later confirmed this when he showed that black holes emit radiation, implying they have a temperature and thus, by the laws of thermodynamics, an entropy. This insight laid the groundwork for the holographic principle. If all the information that falls into a black hole is somehow stored on its surface, then perhaps space itself works this way. The ADS/CFT correspondence, developed by Juan Maldacena, provided the first mathematical realization of this idea. It showed that a certain kind of string theory in a five-dimensional anti-de Sitter, ADS, space is equivalent to a conformal field theory, CFT, on its four-dimensional boundary. In simpler terms, a higher-dimensional gravitational theory can be fully described by a lower-dimensional quantum theory without gravity. While our universe is not anti-de Sitter space, it's actually expanding, not contracting. The principle opens a path to understanding quantum gravity. The black hole's event horizon may not be just a point of no return. It may be a screen, a ledger, a boundary that contains the full description of everything that has ever entered. If this is true, then black holes don't destroy information after all. Instead, they may scramble it, repackage it in incomprehensible ways, and store it on their surface in a kind of cosmic hard drive. This possibility offers a potential resolution to the information paradox. It reconciles the irreversible absorption of matter with the reversibility of quantum mechanics. The information is not gone, it's encoded in the fluctuations of the event horizon. Imagine, then, that you are watching a black hole from a safe distance. You see a star spiral inward, its light redshifting, its matter stretching. As it crosses the event horizon, it seems to vanish. But what if, in some hidden quantum code, the entire history of that star is now etched onto the surface of the black hole? Every atom, every vibration, every detail may still exist, not inside, but on the edge. This leads to a radical notion. The interior of the black hole might not be real in the way we think. It may be a holographic illusion, a projection from the two-dimensional boundary. From the perspective of an external observer, the interior never truly forms. All processes are described entirely by the physics on the surface. And if this is true for black holes, could it be true for the universe at large? Could our entire cosmos be the interior of a gigantic hologram, encoded on some distant, cosmic boundary we cannot see? This idea, while speculative, has fascinated physicists and philosophers alike. It suggests that dimensions are emergent, not fundamental, that reality is a kind of information processing, and we are patterns on a cosmic screen. This perspective changes everything. It reshapes our questions about space and time. It suggests that locality, the idea that events happen in specific places, is not a fundamental feature of reality. Instead, everything may be interconnected through hidden correlations, and the apparent separation of objects may be an illusion. Even the structure of time could be different. In holographic models, time might not be an absolute dimension but an emergent phenomenon. The directionality of time, its arrow from past to future, could be tied to the way information is organized and decoded. And yet, as profound as these ideas are, they remain theoretical. We don't yet have empirical proof that the holographic principle holds in our universe. The mathematics is complex, and the physical consequences are subtle. But progress is being made. Simulations and analog systems are being explored in laboratories. Physicists are devising experiments to test the implications of holography, perhaps through gravitational waves or through the quantum structure of space itself. The event horizon, once thought to be a simple boundary, has become a cosmic Rosetta Stone, a place where quantum information, gravity, and geometry converge. If it truly acts like a hologram, then the universe is not as it seems. It is deeper, stranger, and more intricate than any fiction. The event horizon may not be the end. It may be the key. simulated horizons and laboratories. While black holes lie far beyond the reach of our current spacefaring capabilities, scientists have begun exploring their behaviors through an unexpected method: simulation. Not digital simulations alone, but physical analogs created in earthly laboratories. These aren't just thought experiments or graphic visualizations. They are real-world systems, engineered to mimic the behavior of black hole event horizons, allowing us to study the extreme physics of these cosmic monsters in an environment where equations can be tested, and hypotheses can be observed in action. One of the most successful approaches in simulating event horizons relies on Bose-Einstein condensates, a state of matter where atoms are cooled to temperatures near absolute zero. At this frigid point, matter behaves less like a collection of individual particles and more like a unified quantum entity, a single wave-like structure. In this quantum playground, researchers can manipulate the speed of sound in such a way that it creates a boundary analogous to an event horizon. Inside the simulated black hole, sound waves cannot escape, mirroring how, beyond a real event horizon, not even light can break free. The idea is elegant. If one part of the condensate flows faster than the speed of sound, and the other moves slower, a boundary forms. Any phonon, a quantum of sound, created past that boundary cannot escape back into the slower-flowing region. It is trapped, just as photons are trapped inside a black hole. This creates an acoustic black hole. And while no actual mass is involved, and nothing is being gravitationally crushed, the math describing the horizon's effects bears a striking resemblance to Einstein's equations of general relativity. But why go to such lengths to simulate something so distant and extreme? Because this gives us a testbed for ideas that would otherwise remain untested. Take Hawking radiation, for example. Stephen Hawking's revolutionary insight that black holes should emit radiation due to quantum effects near the event horizon has, to date, never been directly observed in space. The radiation is too faint, too subtle to detect with our instruments. But in a laboratory-created horizon, conditions can be tightly controlled, and the effects become measurable. In 2010, physicist Jeff Steinhauer at the Technion in Israel succeeded in observing phenomena in a Bose-Einstein condensate that mimicked the predicted Hawking radiation. It wasn't direct proof, but it was the first step toward experimental confirmation. And that's just the beginning. Other experimental setups use optical fibers, where light pulses can create regions that act like horizons. When a high-intensity laser pulse travels through a nonlinear fiber, it changes the refractive index of the medium behind it. This can trap slower photons, forming a kind of optical horizon. Under the right conditions, the interaction of light and the induced medium creates measurable signals that resemble Hawking radiation. Yet another model uses superfluid helium, a bizarre substance that flows without viscosity. In such a medium, disturbances can behave like they are in curved spacetime. Similar to the acoustic analogs, these setups help test gravitational behavior using wave propagation. Each of these systems is limited, of course. They don't replicate the full range of black hole physics. They can't generate the immense gravity, the spacetime curvature, or the singularity at the core. But they offer something invaluable: accessibility. They give physicists a way to tweak parameters, observe behaviors, and measure outcomes in ways that are impossible with distant astrophysical black holes. More importantly, these simulations provide insights into how quantum mechanics and gravity might interact. By studying how horizons behave in quantum systems, we begin to bridge the gap between Einstein's geometric description of gravity and the probabilistic nature of the quantum world. The hope is that one day, these analog systems might point the way toward a true quantum theory of gravity. What makes this approach so fascinating is that it transforms the black hole from a mysterious cosmic monolith into a laboratory artifact. It brings the event horizon, once an unreachable edge of the universe, into the confines of a human-made experiment. We go from peering at distant X-ray flares and gravitational waves to controlling black hole-like environments with lasers and supercooled gases. Even more intriguing is the idea that if Hawking radiation can be verified in these systems, it not only validates part of black hole thermodynamics, it also tells us something deep about the nature of reality itself. If event horizons are thermodynamic systems, governed by entropy and temperature, then space itself may be emergent, a macroscopic effect of something more fundamental, perhaps even information. This returns us to the holographic principle. These simulations give us a chance to test whether horizons are places where space and time begin to unravel, not because of gravity alone, but because of the strange interplay between quantum information and curved geometry. The implications spill far beyond black holes. If we can simulate event horizons, can we also simulate other space-time phenomena? Wormholes, quantum foam, even the early universe itself? Already, researchers are investigating ADS/CFT dualities in condensed matter systems and building tabletop analogs of inflationary cosmology. The very structure of reality is becoming something that can be modeled, manipulated, and explored. One day, it may even be possible to simulate the inside of a black hole, not by entering it, but by recreating its causal structure in a controllable quantum system. We might witness, in a lab, the birth and death of virtual particles, the stretching of time near a horizon, or even the resolution of paradoxes that have plagued physics for decades. In this way, simulated event horizons are not just scientific curiosities. They are gateways, not to another place in space, but to another level of understanding. A portal to a deeper dimension of knowledge. In the sterile quiet of a lab, surrounded by wires, lasers, and sensors, humanity may yet unlock the secrets of the darkest hearts of the cosmos. Inside the event horizon, can anything escape? The event horizon is often described as the point of no return. Once an object crosses this invisible boundary surrounding a black hole, it is believed to be lost to the universe forever, its destiny sealed by the immense gravitational pull of the singularity at the center. But what actually happens inside the event horizon? And is there any conceivable way for anything to escape from within it? To answer these questions, we must first understand what the event horizon truly is. It is not a physical surface like the crust of a planet. It is a mathematical boundary, a threshold in space-time beyond which all paths inexorably lead inward. The escape velocity at this boundary equals the speed of light. Thus, nothing, not even photons, can resist the black hole's pull once they have passed this boundary. From an external observer's perspective, an object falling toward a black hole appears to slow down as it approaches the event horizon. Time dilation becomes extreme, and the object's image freezes, redshifts, and fades away. But this is an illusion created by relativity. To the falling object itself, time flows normally, and the crossing of the horizon is uneventful. There's no sudden jerk, no wall, no sensation of reaching a boundary. Inside the event horizon, however, space-time undergoes a radical transformation. In a sense, space and time switch roles. The radial direction, the one leading toward the singularity, becomes timelike. This means the future lies at the singularity itself. No matter which direction one tries to move, the curvature of space-time forces every path to lead to the singularity. It's not that one is being pulled toward it in the traditional sense, it's that the singularity becomes as unavoidable as tomorrow. Just as you cannot choose not to move forward in time, you cannot choose not to move inward within the event horizon. This raises an important question. Is it truly impossible to escape from the inside? According to general relativity, yes. The equations show that all timelike and null geodesics, the paths that objects and light follow, terminate at the singularity. There is no trajectory that leads outward once the event horizon has been crossed. This is a key feature of classical black holes. However, quantum mechanics has a habit of breaking the rules. The phenomenon of Hawking radiation implies that black holes are not entirely black. Over vast timescales, they can lose mass and eventually evaporate. If Hawking radiation is real, and if it somehow contains information about what has fallen into the black hole, then it may be possible, in principle, that some information escapes. This is not the same as an object climbing back out of the event horizon, but it raises the possibility that the contents of a black hole are not truly lost to the universe. Moreover, some speculative theories propose wormholes or Einstein-Rosen bridges, tunnels in spacetime that could connect one black hole to another, or to a distant part of the universe. If these structures are stable, which remains highly doubtful under classical general relativity, it might be possible for something to fall into a black hole and emerge elsewhere. However, traversable wormholes would require exotic matter with negative energy density, something that has never been observed. Other theories suggest that black holes might bounce, transforming into white holes, theoretical opposites of black holes that expel matter rather than absorb it. In these models, the singularity is not the end of time but a point of transformation. Quantum gravity effects might cause the black hole to shrink and explode, ejecting the matter and energy it once devoured. But this too remains hypothetical. Then there's the firewall hypothesis, which posits that a searing wall of high-energy particles exists at the event horizon, incinerating anything that touches it. If true, the interior of the black hole might not even exist in the traditional sense. But this controversial idea remains unproven and hotly debated. Let us consider the perspective of the infalling observer. Suppose you're in a spaceship and you cross the event horizon. To you, time appears to flow normally. You see the stars behind you become distorted and redshifted, but you feel no sudden shock as you pass the boundary. Depending on the size of the black hole, you may not even be crushed immediately. In supermassive black holes, tidal forces at the horizon are weak, and you could survive for a time, drifting toward the singularity. Inside, you might even be able to study the interior structure, if such a thing can be said to exist. But you could never send a signal back out. Your story would end at the singularity, a point of infinite density and zero volume, where the known laws of physics break down. But the universe is not content to leave these questions unanswered. Theoretical physicists continue to probe the interior of black holes using tools from string theory, loop quantum gravity, and ADS/CFT correspondence. These approaches attempt to unify general relativity and quantum mechanics and offer potential models where the singularity is resolved or avoided altogether. Some suggest that space inside a black hole may be non-singular, or that it may harbor a rich and complex structure, possibly even an entire universe. One of the most fascinating proposals comes from the idea of black hole complementarity, which we'll explore more deeply later. It suggests that the interior and exterior descriptions of a black hole are not separate realities but complementary perspectives. From the outside, nothing escapes. From the inside, one experiences a seamless journey. Both are true in their own reference frames, but trying to combine them into a single picture leads to paradoxes. So, can anything escape from inside the event horizon? In the classical view, the answer is no. But as we delve deeper into the quantum realm, the answer becomes less clear. Information might escape. New physics might emerge. Singularities might be avoided. And the true nature of space and time may turn out to be far more flexible, and far stranger, than we ever imagined. The event horizon, once seen as the ultimate boundary, may be just another veil, one that, when lifted, reveals not destruction, but transformation. Black hole complementarity. Black hole complementarity is a radical idea born from the need to reconcile the strange and seemingly contradictory observations about black holes. It challenges our classical understanding of physics and suggests that different observers may perceive completely different realities when it comes to black holes, and yet both perceptions could be valid. It is a bold proposal, one that arose in the context of preserving the unitarity of quantum mechanics in the face of the black hole information paradox. To understand black hole complementarity, we must first revisit the conflict that gave rise to it, the black hole information paradox. In quantum mechanics, information about a physical system is preserved over time. That is, if you know the exact state of a system at one point, you should, in theory, be able to determine both its past and its future. This principle, known as unitarity, is a cornerstone of quantum theory. However, black holes seem to defy this principle. When matter falls into a black hole, it appears to vanish beyond the event horizon. According to classical general relativity, this information is lost forever. But if the black hole eventually evaporates through Hawking radiation, as quantum theory predicts, and that radiation is purely thermal, meaning it carries no information, then the original data about what fell in is seemingly destroyed. This loss of information would violate the fundamental rules of quantum mechanics. This paradox created a crisis in theoretical physics. To resolve it, physicists proposed that Hawking radiation might somehow encode the information of the infalling matter, albeit in a highly scrambled and diffuse form. But that presented a new puzzle. If the information is encoded in the radiation outside the event horizon, does that mean it never really crossed the horizon? And if it did cross, how could that same information also remain accessible at the boundary? Enter black hole complementarity. Proposed by Leonard Susskind and others, black hole complementarity posits that there is no single, global viewpoint that can simultaneously describe both the infalling and the external observer's experience of the black hole. Instead, these two perspectives are complementary, like the wave-particle duality of quantum mechanics. From the outside, all the information about an object that falls into a black hole is somehow smeared across the event horizon, and later leaks out via Hawking radiation. From the inside, the object continues unhindered into the interior of the black hole, unaware that anything unusual has happened at the horizon. But here's the twist: no single observer can witness both realities. An outside observer can never see the interior, and an infalling observer cannot send information back out. This restriction ensures that there is no contradiction, because no one can test both views simultaneously. In a sense, the principle protects the consistency of physics by forbidding any overlap between the perspectives. Imagine a person falling into a black hole. To a distant observer, they appear to slow down and freeze at the event horizon, never quite crossing it. The information about them becomes encoded in the horizon itself. But from the person's point of view, they pass the horizon without incident, continuing on a journey that leads to the singularity. Both stories are true, but only from their respective frames of reference. This concept draws inspiration from the holographic principle, which we'll explore in more detail later. The holographic principle suggests that all the information contained within a volume of space can be described by data encoded on the boundary of that space. In the case of black holes, the event horizon acts as a two-dimensional surface that encodes the three-dimensional data of the black hole's interior. Black hole complementarity is a powerful idea because it allows physicists to preserve both the equivalence principle, a pillar of general relativity that states an observer in free fall experiences no special effects at the event horizon, and unitarity, the requirement of information conservation in quantum mechanics. It's a way to have our cake and eat it too, by assigning different realities to different observers, each consistent within their own frame. However, this elegant resolution has been challenged by new developments, most notably the firewall paradox. This paradox arises when we combine the principles of unitarity, the equivalence principle, and the assumption that Hawking radiation is entangled with the interior of the black hole. The math seems to show that all three cannot be true at once. If Hawking radiation carries away information, then the entanglement between the horizon and the interior must be broken, leading to the formation of a high-energy firewall at the event horizon. This would violate the equivalence principle and destroy anything falling in. So, which principle do we sacrifice? Proponents of black hole complementarity argue that firewalls may not be necessary. Perhaps the paradox arises because we are trying to describe both interior and exterior realities using the same framework, when in fact they are fundamentally complementary. In this view, quantum information is not duplicated, nor is it destroyed. Instead, it is encoded in such a way that the apparent duplication is never observable. Think of it like a quantum version of Schrödinger's cat. To one observer, the cat is alive, to another dead. But the two observers cannot communicate their results without destroying the delicate quantum state. In black hole complementarity, the information is both outside and inside the black hole, but no single observer can ever compare notes. This principle may seem strange, even contradictory. But quantum mechanics has taught us time and again that our classical intuitions do not always apply at the smallest scales. Complementarity might be the key to resolving some of the deepest puzzles of black hole physics, by acknowledging that different observers can experience radically different versions of reality, without violating the underlying laws of physics. Black hole complementarity does not offer a final answer. It is more of a philosophical stance than a fully fleshed-out theory. Yet it has profoundly influenced the way physicists think about horizons, information, and the nature of reality. As our understanding of quantum gravity advances, we may find that complementarity is not just a curious feature of black holes, but a universal property of spacetime itself. The stretching of spacetime itself. When we think about black holes, one of the most hauntingly beautiful aspects is the way they warp spacetime, twisting it, bending it, and in some ways, stretching it beyond recognition. This phenomenon, known as gravitational stretching, is not just a metaphor, it's an actual warping of the fabric of the universe, dictated by Einstein's general theory of relativity. But at the edge of a black hole, the event horizon, this stretching becomes extreme, approaching the very limits of physical comprehension. To grasp this, we must return to Einstein's idea that gravity is not a force in the classical sense. Instead, it is the manifestation of curved spacetime caused by mass and energy. Think of a stretched rubber sheet. Place a bowling ball in the center, and the sheet deforms. Now roll a marble nearby. It moves not because of some invisible force pulling it, but because the shape of the sheet directs its path. In the universe, that sheet is spacetime, and massive objects like stars and planets curve it around them. Now imagine the most extreme case. A black hole, an object so dense that it curves the space-time fabric into a deep well, so steep that not even light can escape. As you approach the event horizon, the curvature becomes more intense, and space-time begins to behave in ways that defy classical logic. One of the key manifestations of this curvature is the phenomenon of spaghettification, which we've discussed earlier. This is caused by the tidal stretching of space-time. As you get closer to the black hole, the difference in gravitational pull between your head and your feet becomes so great that you would be stretched into a long, thin filament. But this tidal stretching is just one aspect of a larger cosmic ballet. On a larger scale, the stretching of spacetime near a black hole also leads to time dilation, the slowing of time relative to distant observers. If you watched a clock falling toward a black hole, it would appear to tick more slowly, eventually freezing as it reached the event horizon. This is not an illusion, but a real, measurable consequence of the way gravity affects time. For the person falling in, time flows normally, but to the outside universe, their clock appears to slow and halt. This is where the geometry of spacetime becomes truly exotic. Near the event horizon, the coordinate system we use to describe space and time essentially flips. Inside the event horizon, moving forward in time is the same as moving deeper into the black hole. You can no longer stand still or move away from the center. Even if you travel at the speed of light, you are inevitably pulled toward the singularity. It's not a matter of falling, it's a matter of future-directed motion. The singularity is in your future, just like tomorrow. But the stretching of space-time doesn't stop at spaghettification or time dilation. On a quantum level, the very fabric of space-time may be undergoing fluctuations, tiny warps and waves, known as quantum foam, constantly bubbling at the smallest scales. Near a black hole, this foam could be amplified, interacting with the intense curvature in unpredictable ways. Some theories suggest that the event horizon itself may not be a smooth boundary, but a fluctuating surface, writhing with quantum activity. This brings us to a deeper idea. What if the stretching of spacetime near a black hole is so extreme that it literally tears apart the structure of the vacuum itself? In classical physics, the vacuum is empty space. But in quantum field theory, it is a seething ocean of virtual particles, constantly popping in and out of existence. Near the event horizon, these fluctuations could be magnified, giving rise to effects like Hawking radiation and possibly even the creation of particles from nothing. The stretching of space-time also poses profound questions for cosmology. Some researchers believe that the intense warping near black holes could give birth to new regions of space-time, perhaps even new universes. These ideas, though speculative, suggest that black holes might be more than just endpoints. They could be cosmic gateways or seeds of creation. In loop quantum gravity, for example, space-time is thought to be made of discrete loops, tiny quantum units of area and volume. As the space-time fabric stretches and curves around the black hole, it may reach a point where these loops cannot stretch further, creating a bounce instead of a singularity. This could lead to a white hole, or even a new expanding region of spacetime on the other side. Another fascinating implication of stretched spacetime is the idea that information might be encoded in the very stretching itself. If information about falling matter is preserved, perhaps it is inscribed into the geometric distortions of the horizon. This concept ties back to the holographic principle, which posits that the entire volume of space inside a black hole could be described by information stored on the horizon's surface. Moreover, recent studies in quantum chaos suggest that the stretching of spacetime might serve as a kind of cosmic amplifier for small differences in initial conditions. This chaotic behavior means that tiny quantum fluctuations near the horizon could grow and evolve in wildly different ways, leading to unpredictable outcomes. The event horizon becomes not just a boundary, but a frontier of chaos and transformation. In the framework of ADS/CFT correspondence, a theory that connects gravity in a curved space, like that around a black hole, with a quantum field theory on the boundary, this stretching of spacetime is essential. It underpins the duality between gravitational physics and lower-dimensional quantum systems. This could mean that the complex, multidimensional warping near a black hole is mirrored by simpler quantum processes on a flat surface, a profound insight into how the universe might encode reality. The stretching of spacetime near a black hole is more than just a curious phenomenon. It is a window into the fundamental nature of gravity, quantum mechanics, and reality itself. It challenges our understanding of time, space, causality, and even the limits of knowledge. As we explore this stretching in more detail, both theoretically and experimentally, we may uncover new principles that reshape physics as we know it. Perhaps black holes are not so much cosmic destroyers as cosmic teachers, revealing the limits of our models, the beauty of geometry, and the potential unity of the forces that govern the universe. Chaos and the edge of predictability. As the stretching of spacetime near a black hole's event horizon continues to push the boundaries of physics, we encounter a fascinating and deeply unsettling concept: chaos. In many physical systems, chaos refers to a sensitive dependence on initial conditions. Small differences at the start lead to wildly divergent outcomes over time. This phenomenon, often called the butterfly effect, is not just an abstract mathematical idea. It fundamentally challenges our ability to predict the future in certain contexts. Near the event horizon of a black hole, the interplay of gravity, quantum mechanics, and relativistic effects produces an environment ripe for chaos. The intense gravitational gradients combined with quantum fluctuations mean that the state of matter and information near the horizon can evolve unpredictably. This chaos manifests in several ways. First, the trajectories of particles and light rays near the horizon can be extremely sensitive. Even the slightest perturbation, caused by passing radiation, incoming matter, or quantum jitter, can cause a particle's path to diverge dramatically. Over time, these small changes amplify, leading to complex, unpredictable behavior. Second, the chaotic nature of black hole horizons is intimately tied to the information paradox. The question of whether information that falls into a black hole is lost forever or somehow preserved. If the horizon behaves chaotically, then even tiny bits of information could be scrambled beyond recognition. This scrambling suggests that while information might not be destroyed, it becomes practically irretrievable, locked in a chaotic quantum whirlpool. The mathematical tools used to describe chaos near black holes often come from the field of quantum chaos, which merges classical chaos theory with quantum mechanics. One of the central challenges is that black holes exist at the intersection of these two regimes. They are governed by classical gravity, Einstein's equations, but also influenced by quantum effects at very small scales. Interestingly, the chaos near the event horizon also connects with the so-called fast scrambling conjecture. This conjecture suggests that black holes are the fastest scramblers of information in the universe, rapidly mixing any incoming data so that it becomes nearly impossible to isolate or reverse. This property makes black holes unique quantum systems and hints at a deep link between gravity and information theory. Chaos also challenges the classical picture of determinism. In classical physics, if you know the initial conditions perfectly and the laws governing the system, you can predict its future exactly. However, in chaotic systems, the tiniest uncertainty makes long-term prediction impossible in practice. When you add quantum uncertainty on top of this, the event horizon becomes a zone where predictability reaches its ultimate limits. This edge of predictability raises profound philosophical questions. If the horizon marks a boundary where physics becomes fundamentally uncertain, what does that say about the nature of reality? Are black holes gateways to indeterminism, where the universe's deepest secrets are obscured behind an impenetrable veil of chaos? Moreover, chaos near the horizon has practical implications for astrophysics. It influences how black holes interact with their surroundings, how accretion disks behave, and how jets of high-energy particles are launched. Understanding this chaotic environment is essential to interpreting observations from telescopes and gravitational wave detectors. In recent years, theoretical physicists have employed advanced computational models to simulate the chaotic dynamics near black hole horizons. These simulations reveal a turbulent, unpredictable environment where classical intuition breaks down, and quantum gravity effects become essential. But chaos near a black hole's event horizon is not merely a destructive force. It could also be a creative one. Some theories propose that this chaos leads to the emergence of new physics, new particles, or even new regions of space-time. It may be the cosmic crucible where fundamental laws are forged and transformed. Thus, the edge of predictability at the black hole horizon stands as a boundary between order and disorder, between known physics and the unknown, between the classical and quantum worlds. It beckons scientists and philosophers alike to explore the mysteries hidden in this turbulent frontier. Event horizon as a quantum boundary. The event horizon of a black hole is often depicted as a simple, invisible surface, a point of no return where gravity's pull becomes so strong that not even light can escape. But modern physics suggests this boundary is far from a mere geometric line in space. Instead, it acts as a profound quantum boundary, a place where the classical descriptions of space and time collide head-on with the unpredictable, probabilistic nature of quantum mechanics. At this juncture, the fabric of reality itself seems to shimmer and blur, governed by quantum fluctuations and entanglements rather than smooth geometry. This quantum boundary concept challenges our classical intuition. While classical general relativity treats the event horizon as a clean mathematical surface, an apparent edge to the black hole, quantum theory hints that this surface may be fuzzy, dynamic, and filled with intricate microstates. These microstates correspond to the quantum degrees of freedom that encode the information of everything swallowed by the black hole. From this perspective, the event horizon is not just a boundary for matter and light, but also a holographic screen storing the black hole's entire quantum information content. This holographic principle, pioneered by physicists like Gerard T. Hooft and Leonard Susskind, revolutionizes how we think about the event horizon. It posits that all information about the 3D interior of a black hole can be encoded on its 2D boundary, its event horizon, much like a hologram stores a three-dimensional image on a two-dimensional surface. This means the event horizon functions as a quantum memory bank, a vast repository where the black hole's identity is preserved, albeit in a highly scrambled form. The quantum boundary is further complicated by the presence of intense gravitational fields near the horizon. These fields warp spacetime so severely that they magnify quantum fluctuations, temporary changes in energy levels that spontaneously pop in and out of existence according to the Heisenberg uncertainty principle. The event horizon becomes a boiling sea of virtual particles and antiparticles, a quantum foam where space and time themselves become turbulent and unstable. At this horizon, the interplay between gravity and quantum mechanics leads to surprising consequences. For example, the traditional notion that nothing can escape a black hole's grasp is challenged by quantum effects like Hawking radiation, which arises precisely due to this seething quantum activity at the event horizon. Thus, the event horizon as a quantum boundary is not an absolute barrier but a permeable, probabilistic interface where the laws of physics transform and merge. Moreover, recent theoretical developments suggest that the event horizon may serve as a boundary not just in spacetime but also in the flow of quantum information. Information entering the black hole may become encoded on the horizon's surface and then slowly radiated back out in a scrambled form, potentially resolving the long-standing information paradox that has puzzled physicists for decades. This quantum boundary role of the horizon is central to modern attempts to reconcile general relativity with quantum theory into a unified framework. The quantum boundary also raises questions about locality and causality. In classical physics, events separated in space and time are independent, and cause precedes effect. But near a quantum boundary like the event horizon, these notions blur. Quantum entanglement, a phenomenon where particles become interconnected regardless of distance, can link states inside and outside the horizon in non-local ways, hinting at a more subtle causal structure than classical intuition suggests. In this light, the event horizon becomes a natural laboratory to probe the foundations of reality. Its quantum boundary conditions test the limits of our current understanding and may guide the development of a complete theory of quantum gravity. Such a theory would describe how space-time geometry emerges from underlying quantum states and how classical gravity is just a macroscopic manifestation of deep quantum processes occurring at boundaries like the event horizon. Experimental verification of these ideas remains challenging due to the extreme environments involved, but analogs of event horizons have been created in laboratory settings, using systems like ultra-cold atoms and optical fibers to simulate horizon-like conditions. These experiments shed light on how quantum boundaries might operate and help physicists refine their models of black hole horizons. Ultimately, considering the event horizon as a quantum boundary invites us to rethink the nature of space, time, and information. It suggests that what we perceive as empty, smooth space may be a dynamic, information-rich surface bristling with quantum activity. This perspective transforms black holes from cosmic abysses of destruction into complex quantum systems whose boundaries encode the deepest secrets of the universe. This view also dovetails with the broader idea that the universe itself may be holographic, with the information content of our entire cosmos encoded on a vast cosmic horizon. Black hole event horizons thus become microcosms of this grand holographic principle, providing a window into the interplay between gravity, quantum theory, and the nature of reality. Physicists continue to debate and explore these concepts, developing mathematical frameworks such as the ADS/CFT correspondence, which links gravitational systems in higher dimensional spacetimes to quantum field theories on their lower dimensional boundaries. These advances bring us closer to understanding how the quantum boundary at the event horizon connects to the fabric of the universe itself. The event horizon as a quantum boundary is a concept rich with implications and mysteries. It challenges the classical picture of black holes, reveals the quantum nature of gravity, and provides crucial clues toward a unified theory of physics. As research progresses, the event horizon may reveal not just the limits of physics but also its most profound truths. Gravitational redshift at the horizon. As one approaches the event horizon of a black hole, one of the most striking phenomena predicted by Einstein's theory of general relativity becomes apparent: gravitational redshift. This effect describes how light, or any electromagnetic radiation escaping from a region of strong gravitational field loses energy, resulting in an increase in its wavelength, or redshift. Near a black hole's event horizon, gravitational redshift reaches extremes that challenge both our observational capabilities and theoretical understanding. To grasp gravitational redshift near a black hole, we must first understand how gravity affects light. According to general relativity, gravity is the curvature of spacetime caused by mass and energy. When light tries to escape from a strong gravitational field, it must climb out of this curvature, expending energy in the process. However, since photons travel at the speed of light and cannot lose energy in the traditional sense, their frequency diminishes, causing their wavelength to stretch towards the red end of the electromagnetic spectrum. This redshift grows more severe the closer the light source is to the massive object. At the event horizon itself, this gravitational redshift theoretically becomes infinite. If an object were to emit light precisely at the event horizon, that light would be infinitely stretched, meaning it would lose all its energy before reaching an outside observer. As a result, signals from just at or inside the event horizon can never reach an external observer, which is why black holes appear black in the first place. For an observer far from the black hole, objects falling toward the event horizon seem to slow down and fade. Due to gravitational redshift, the frequency of light emitted by the infalling object drops continuously, and the object appears to freeze just outside the horizon, becoming dimmer and redder until it vanishes from view. This freezing effect is not due to the object actually stopping, but rather how the intense gravity distorts the flow of time and the propagation of light. This phenomenon intertwines deeply with the concept of time dilation near a black hole. Because gravity warps spacetime, time itself runs slower near the event horizon compared to an observer far away. As a result, gravitational redshift is also a temporal effect. The light from an infalling object stretches out over longer intervals, causing it to appear increasingly redshifted and delayed. The gravitational redshift near the horizon affects all forms of radiation, including X-rays, gamma rays, and even gravitational waves. For astrophysicists, this redshift provides a crucial tool to probe the environments around black holes, helping to infer properties such as mass, spin, and accretion dynamics. By measuring the shift in spectral lines emitted from material near the horizon, scientists can reconstruct the intense gravitational fields and gain insights into the behavior of matter under extreme conditions. However, measuring gravitational redshift near the event horizon is no trivial task. The immense gravitational fields also warp the trajectories of photons, bending light paths and creating phenomena like gravitational lensing. This bending means that light escaping from just outside the event horizon can follow curved paths around the black hole, producing complex and distorted images. The Event Horizon Telescope's groundbreaking imaging of the black hole in M87 relied heavily on understanding these relativistic effects, including gravitational redshift, to decode the light reaching Earth. Another subtlety of gravitational redshift near black holes is its interplay with the black hole's spin and the frame dragging effect. Rotating black holes, described by the Kermetric, drag spacetime around with them. This frame dragging alters how light's frequency shifts depending on the direction of emission relative to the black hole's rotation. Photons emitted in the direction of spin experience different redshifts than those emitted against it, adding complexity to the observed spectra and challenging models attempting to decode black holes' surroundings. The infinite redshift at the event horizon also influences the way physicists think about the boundary itself. Because no signal can escape, the horizon acts as a causal boundary, defining the limits of observable phenomena. This boundary's properties are not just mathematical curiosities. They hold physical consequences that ripple through black hole thermodynamics, quantum theory, and the search for a theory of quantum gravity. Gravitational redshift also connects to the behavior of virtual particles near the horizon, a key aspect of Hawking radiation. The intense gravitational gradient stretches quantum fluctuations, allowing one particle of a pair to escape as radiation while the other falls into the black hole. This process depends on the redshifting of energy levels and demonstrates how gravitational redshift is deeply embedded in the quantum mechanics of black holes. From a philosophical standpoint, gravitational redshift near the event horizon challenges our notions of observation and reality. It illustrates how extreme gravity can distort time and space to such a degree that the flow of information becomes asymmetric. What an infalling observer experiences is vastly different from what a distant observer sees. This divergence calls into question the universality of events and underlines the importance of the observer's frame of reference in relativistic physics. Interestingly, gravitational redshift also implies a fundamental limit on what can be known about the interior of a black hole. Because signals carrying information are indefinitely redshifted and delayed, the internal processes become hidden behind a veil of warped spacetime. This boundary of knowledge resonates with the broader paradoxes of black hole physics, such as the information paradox, and motivates new ideas about how information might be preserved or transformed at the horizon. In the broader cosmological context, gravitational redshift has analogues in phenomena such as cosmological redshift, where light from distant galaxies stretches due to the expansion of the universe. Both phenomena illustrate the deep relationship between gravity, motion, and the behavior of light, a relationship that black holes crystallize in their most extreme form. Future observational campaigns promise to deepen our understanding of gravitational redshift near event horizons. Advances in X-ray astronomy, gravitational wave detection, and high-resolution imaging will allow scientists to study matter as it spirals into black holes with unprecedented detail. These observations will not only confirm predictions of general relativity but may also reveal deviations pointing toward new physics beyond Einstein's theory. Moreover, the interplay of gravitational redshift with quantum effects near the event horizon provides a fertile ground for theoretical exploration. By studying how redshift affects quantum states and entanglements, physicists hope to unravel the quantum structure of spacetime and the fate of information swallowed by black holes. In summary, gravitational redshift at the event horizon is a multifaceted phenomenon linking gravity, quantum mechanics, and observational astrophysics. It encapsulates how the fabric of spacetime bends and stretches under extreme conditions, shaping the appearance and behavior of black holes from the perspective of the universe at large. Understanding this effect is key to unlocking the mysteries of black holes and the fundamental laws governing our cosmos. Bouncing cosmologies, white hole theories. In the grand quest to understand black holes and their enigmatic boundaries, one of the more intriguing and speculative ideas revolves around the concept of bouncing cosmologies and the possibility of white holes. While black holes are regions of space where matter and energy collapse inward, white holes are theoretical constructs that would act as the time reversal counterpart, regions from which matter and energy emerge, but nothing can enter. This concept opens a fascinating dialogue about the nature of the universe, the fate of information, and whether black holes could, in some sense, be portals or gateways to other regions of spacetime. Bouncing cosmologies come into play when considering the extreme conditions near or inside black holes. Traditional general relativity predicts that at the core of a black hole lies a singularity, a point where densities and curvature become infinite, and the known laws of physics break down. However, singularities pose significant conceptual and mathematical challenges, prompting physicists to explore alternatives where the core might bounce back instead of collapsing indefinitely. One such alternative is the idea that the singularity is replaced by a bounce, a moment when the gravitational collapse halts and reverses, potentially leading to the formation of a white hole. In this scenario, the black hole acts like a cosmic gate, swallowing matter and energy, only to eventually release it through a white hole at a different location or time. This notion is tantalizing because it offers a mechanism for information and matter preservation, addressing some of the paradoxes associated with black holes, such as the information loss paradox. White holes, as solutions to Einstein's equations, have been proposed theoretically since the 1960s. They arise naturally as the time-reverse versions of black holes in certain cosmological models, including the extended Schwarzschild solution known as the maximally extended Kruskal-Zachary's coordinates. In these models, the white hole horizon is the boundary beyond which no matter or information can enter, but everything inside must emerge. However, unlike black holes, white holes have never been observed in nature, and their physical reality remains highly speculative. The concept of bouncing cosmologies ties closely to ideas in quantum gravity and loop quantum cosmology, where the classical singularity is replaced by a quantum bounce due to discrete spacetime structures. In these frameworks, the classical description of continuous spacetime breaks down at Planck-scale densities, and quantum effects cause gravity to become repulsive at extremely high energies. This repulsion halts collapse and initiates expansion, creating a bounce instead of a singularity. If such bouncing behavior is correct, it could mean that black holes are not ultimate sinks of matter but transient stages in a cosmic recycling process. Matter falling into a black hole would be compressed and then expelled through a white hole, potentially in another universe or a distant region of our own universe. This idea intersects with the multiverse hypothesis and speculative cosmologies where black holes birth new universes or serve as conduits for cosmic rebirth. One particularly captivating hypothesis is that our own universe might have originated from a white hole-like bounce inside a parent universe's black hole. This cosmological model, sometimes called the black hole cosmology, suggests a fractal or nested structure of universes, each emerging from the interior of black holes within other universes. Though speculative, this model attempts to unify cosmology and black hole physics, offering profound insights into the origin of space, time, and matter. Another aspect of bouncing cosmologies is their potential to resolve the black hole information paradox. Since white holes theoretically expel information and matter, they provide a natural channel through which information could escape the clutches of black holes, preserving quantum unitarity. This escape mechanism contrasts sharply with classical black hole theory, where information falling beyond the event horizon is thought to be lost forever, violating the principles of quantum mechanics. Theoretical physicists have explored various models incorporating white holes and bounces, including modifications to general relativity and quantum gravity proposals. Some models suggest that the bounce might be accompanied by high-energy phenomena, such as bursts of radiation or energetic particle emissions, potentially detectable as astrophysical signals. Searches for such signals continue, though none have conclusively indicated white hole activity. Despite the conceptual elegance of bouncing cosmologies and white holes, challenges abound. White holes appear unstable in classical general relativity and tend to evaporate rapidly due to quantum effects. Their existence would require finely tuned initial conditions or exotic forms of matter and energy to stabilize. Furthermore, reconciling bouncing cosmologies with observational data and standard cosmological models remains an ongoing challenge. Experimentally, the absence of detected white holes or clear signatures of cosmic bounces keeps these theories in the realm of theoretical speculation. However, advances in gravitational wave astronomy, high-energy astrophysics, and cosmology could shed light on the possible existence of bounces and white hole phenomena. The interplay between bouncing cosmologies and black hole physics also has philosophical implications. It challenges our notions of beginnings and endings, suggesting that cosmic death and rebirth might be cyclical processes embedded in the structure of space-time. This cyclical view contrasts with the traditional linear narrative of cosmic evolution, opening doors to new ways of understanding the universe's origin, destiny, and interconnectedness. Moreover, bouncing cosmologies stimulate fresh thinking about the arrow of time and entropy. Since white holes would expel matter and energy in a highly ordered fashion, they imply a reversal or modification of the thermodynamic arrow of time, which typically dictates increasing entropy. Understanding how bouncing cosmologies reconcile with the second law of thermodynamics is an active area of research, intertwining statistical mechanics, quantum theory, and gravitational physics. In summary, bouncing cosmologies and white hole theories represent some of the most profound and speculative ideas in modern physics. They challenge established paradigms about black holes, singularities, and cosmic evolution, offering glimpses into a universe where death and creation are intertwined, and horizons are not just boundaries but gateways to new possibilities. Though much remains unknown, the pursuit of these ideas pushes the boundaries of human knowledge, inviting us to rethink the fabric of reality itself. The role of entropy and the second law. At the very heart of black hole physics lies the enigmatic relationship between entropy, thermodynamics, and the second law, a foundational principle of physics stating that in an isolated system, entropy never decreases but tends to increase, reflecting the natural progression toward disorder or the arrow of time. Black holes, however, present an extraordinary challenge and opportunity to understand entropy in a cosmic context, linking gravitational collapse, quantum theory, and thermodynamics in ways that have revolutionized physics since the 1970s. Entropy, classically, is a measure of disorder or the number of microscopic configurations corresponding to a macroscopic state. In everyday life, the second law of thermodynamics ensures that heat flows from hot to cold and that systems evolve toward equilibrium. Black holes, with their intense gravity and seemingly irreversible swallowing of matter and energy, initially posed a paradox. They appeared to violate the second law by seemingly erasing information and reducing entropy to zero. After all, the matter falling into a black hole disappeared beyond the event horizon, never to be recovered, suggesting a loss of entropy and information. This paradox was addressed with the groundbreaking insight of physicists Jacob Bekenstein and Stephen Hawking. Bekenstein proposed that black holes themselves must have entropy proportional to the area of their event horizons, a radical idea that extended thermodynamics into the domain of gravity. This entropy, now called Bekenstein-Hawking entropy, implies that black holes are not just gravitational vacuum cleaners but thermodynamic objects with temperature, entropy, and obey laws analogous to those governing heat engines. Hawking's subsequent discovery that black holes emit radiation, now known as Hawking radiation, cemented this thermodynamic viewpoint. The radiation arises from quantum effects near the event horizon, causing black holes to slowly lose mass and evaporate over incredibly long timescales. The emission of Hawking radiation means black holes have a finite temperature, linking quantum mechanics, gravity, and thermodynamics in a profound union. The role of entropy in black hole physics is deeply tied to the area law, where the entropy of a black hole is proportional not to its volume but to the surface area of its event horizon, measured in Planck units. This contrasts with ordinary thermodynamic systems, where entropy typically scales with volume, suggesting that the event horizon encodes all the information about the black hole's internal states. This led to the formulation of the holographic principle, which posits that all the information contained within a volume of space can be described by degrees of freedom on the boundary surface. The second law of thermodynamics has been generalized to include black holes through the generalized second law, GSL. The GSL states that the sum of the entropy outside the black hole plus the entropy of the black hole itself never decreases. This elegant principle preserves the arrow of time and resolves some paradoxes associated with information loss, indicating that although matter disappears behind the horizon, the entropy associated with it is conserved or accounted for in the black hole's horizon area. Understanding entropy also touches on deeper questions about the microscopic nature of black holes. What are the microstates that account for black hole entropy? Unlike ordinary matter, black holes are described by only a few macroscopic parameters: mass, charge, and angular momentum, leading to the so-called no-hair theorem. Yet, the enormous entropy implies an immense number of quantum microstates. This puzzle has motivated approaches in string theory and quantum gravity, where black holes correspond to ensembles of microscopic states, such as strings, branes, or fuzzballs, each encoding the information hidden behind the event horizon. Entropy's role extends beyond black holes to the universe itself. Cosmological horizons, such as the de Sitter horizon in an expanding universe, also possess entropy and temperature, suggesting a deep connection between gravity, quantum mechanics, and thermodynamics at all scales. This interconnectedness hints at a fundamental principle governing space-time, information, and the flow of time itself. The second law also frames debates about black hole evaporation and final states. As a black hole radiates and shrinks, its entropy decreases, seemingly contradicting the second law unless the emitted radiation carries away sufficient entropy. This dynamic is central to resolving the black hole information paradox, where quantum entanglement between emitted radiation and the black hole interior must preserve unitarity and entropy accounting. In the context of entropy, concepts like entanglement entropy and the Page curve arise, describing how the entropy of Hawking radiation evolves over time, initially increasing but eventually decreasing as information is recovered, a key signature of quantum consistency. These ideas intertwine thermodynamics, quantum information theory, and gravitational physics in a rich tapestry of modern research. Moreover, entropy influences the thermodynamic stability of black holes. Large black holes in anti-de Sitter space, for example, can reach thermal equilibrium with their surroundings, exhibiting phase transitions akin to those in ordinary matter. These phenomena provide laboratories for studying quantum gravity via the ADS/CFT correspondence, a holographic duality linking black holes in curved spacetimes with quantum field theories on their boundaries. The role of entropy also leads to provocative philosophical and foundational questions. Since entropy defines the arrow of time, and black holes embody the extreme of gravitational collapse and information storage, they stand at the crossroads of understanding why time flows in one direction and how the fundamental laws of physics reconcile irreversibility with quantum unitarity. Furthermore, the entropy of black holes imposes limits on information processing, computation, and the maximum storage capacity of physical systems, inspiring cross-disciplinary research into quantum information, black hole thermodynamics, and the ultimate laws of nature. In conclusion, the role of entropy and the second law in black hole physics provides a vital key to unlocking the mysteries of the cosmos. From bridging gravity and quantum mechanics to shaping our understanding of information, time, and the universe's fundamental structure, entropy stands as a central pillar in the ongoing exploration of black holes, horizons, and the nature of reality itself. Fuzzballs instead of event horizons. The concept of fuzzballs emerges as a compelling alternative to the traditional view of black holes with sharp event horizons, providing a fresh perspective on the quantum structure of these enigmatic cosmic objects. Rooted in string theory and quantum gravity, the fuzzball proposal suggests that what we have long perceived as a black hole, a singularity surrounded by a smooth event horizon, may instead be a tangled, complex ball of strings and brains, a fuzz of quantum states with no clear-cut boundary. This radical idea challenges and potentially resolves some of the deepest puzzles of black hole physics, including the information paradox and the nature of space-time near the horizon. Classically, a black hole is described by Einstein's general relativity as a region of spacetime from which nothing, not even light, can escape once past the event horizon. Inside this boundary lies a singularity where density and curvature become infinite, and conventional physics breaks down. The event horizon itself is smooth and featureless, a point of no return. However, the fuzzball theory replaces this smooth event horizon with a quantum, extended structure that has no interior in the traditional sense, no singularity hidden within. Instead, the entire mass and information of the black hole are distributed throughout this fuzzball, composed of strings and brains, which are fundamental objects in string theory. One of the central motivations for the fuzzball concept is the black hole information paradox. According to classical theory, information about matter falling into a black hole is lost forever beyond the horizon, violating the principles of quantum mechanics that require information to be preserved. The fuzzball paradigm provides a resolution by arguing that since the event horizon is replaced by a complicated quantum structure, information is not lost behind a smooth boundary but encoded in the fuzzball's extended quantum state. This encoding means that information can, in principle, be recovered, preserving unitarity and aligning black hole physics with the tenets of quantum theory. The fuzzball's structure is extraordinarily rich and complex. In string theory, strings are one-dimensional fundamental constituents of matter, and brains are higher-dimensional analogs. When these strings and brains are arranged in countless ways, they form microstates that collectively represent a fuzzball. Each microstate corresponds to a different quantum configuration, and together, they account for the enormous entropy associated with a black hole, matching the Bekenstein-Hawking formula proportional to the horizon area. This microstate counting is one of string theory's triumphs, offering a microscopic explanation for black hole entropy that eludes classical gravity. Unlike a classical black hole with a well-defined interior and a sharp horizon, a fuzzball has no interior, empty, region. Instead, spacetime ends at the fuzzball's surface, which is highly quantum and lacks a classical geometric description. This challenges our intuitive notions of space and time and suggests that at the Planck-scale, the fabric of spacetime itself becomes fuzzy and granular, not smooth and continuous. This granularity is the essence of the fuzzball, a quantum cloud that replaces the singularity and horizon with a physically extended, information-rich region. The fuzzball idea also has implications for the fate of infalling observers. Instead of crossing a smooth horizon and descending toward a singularity, an observer would encounter the fuzzball's quantum structure, potentially experiencing a violent and chaotic interaction with the dense web of strings and brains. This scenario contrasts sharply with the classical expectation of a no drama crossing at the horizon, raising questions about the equivalence principle and the nature of locality in quantum gravity. Moreover, fuzzballs offer a new lens on Hawking radiation. Rather than being generated by pair production just outside a smooth event horizon, Hawking radiation in the fuzzball picture arises from the quantum dynamics of the fuzzball's surface itself. Because the fuzzball contains the entire quantum information of the black hole, the emitted radiation can carry away information, again addressing the information paradox and ensuring consistency with quantum theory. Despite its elegance, the fuzzball proposal remains theoretical and highly complex. Constructing explicit fuzzball solutions for realistic astrophysical black holes is challenging, and much work remains to understand the full implications and to find observable signatures distinguishing fuzzballs from classical black holes. However, progress in this field has energized quantum gravity research and inspired new ideas about the quantum nature of spacetime. The fuzzball concept also bridges black hole physics with other areas of theoretical physics, including holography and quantum entanglement. In the holographic framework, the fuzzball can be viewed as a boundary state encoding the bulk geometry, linking quantum information on the boundary to the spacetime interior. This resonates with the broader holographic principle and the notion that spacetime geometry emerges from entangled quantum states. Furthermore, fuzzballs challenge the traditional black hole thermodynamics by offering a microscopic foundation for entropy and temperature without invoking singularities or smooth horizons. This reimagining of black holes aligns with the quest for a quantum theory of gravity, where spacetime geometry and matter are unified into a single quantum entity. In summary, the fuzzball proposal presents a bold and intricate alternative to classical black holes, replacing the event horizon with a complex quantum structure that preserves information, resolves paradoxes, and redefines our understanding of spacetime and gravity. While still a developing theory, fuzzballs push the boundaries of physics and open new pathways toward a consistent quantum theory of gravity, offering tantalizing clues about the fundamental nature of the universe. Firewall versus smooth horizon, the battle of theories. The debate over the nature of the event horizon has evolved into one of the most intense and fascinating battlegrounds in modern theoretical physics. At the heart of this debate is the clash between two competing visions, the firewall hypothesis and the smooth horizon scenario. Both attempt to reconcile the paradoxes that arise when quantum mechanics and general relativity meet at a black hole's boundary, yet they paint starkly different pictures of what an observer would experience at the event horizon. According to classical general relativity, the event horizon is a smooth, uneventful surface. An observer falling freely into a black hole should notice nothing unusual upon crossing the horizon, a consequence known as the equivalence principle, which states that local physics in free fall should resemble that of flat spacetime. This, no drama, assumption preserves the familiar intuition of spacetime's continuity and smoothness, suggesting that the horizon is a perfectly normal region of space despite the black hole's deadly reputation. However, the firewall paradox, first proposed around 2012 by physicists Almhiri, Marov, Polchinski, and Sully, collectively known as AMPS, challenges this serene vision. They argued that to preserve the principles of quantum mechanics, particularly unitarity, and the no-cloning theorem, the horizon cannot be smooth. Instead, it must be replaced by a searing firewall, a zone of intense high-energy radiation that would incinerate any infalling observer the moment they reached it. This idea sharply contradicts the equivalence principle and implies a radical departure from classical expectations. The firewall paradox arises from attempts to resolve the black hole information paradox, which questions how information about infalling matter can be preserved when the black hole evaporates through Hawking radiation. To reconcile quantum information preservation with the smooth horizon picture, contradictions appear. AMPS proposed that these contradictions could only be resolved if the horizon becomes a highly energetic boundary, this firewall, where quantum entanglement between the black hole's interior and exterior is broken, destroying the smoothness of spacetime at the edge. This proposition sparked fierce controversy. Many physicists found the idea of a firewall unpalatable because it undermines the equivalence principle, a cornerstone of Einstein's theory of general relativity. If firewalls exist, they would represent a fundamental breakdown of our understanding of gravity and spacetime, forcing a reassessment of the very fabric of the universe at the smallest scales. The firewall scenario demands that something dramatic happens at the horizon, fundamentally altering the nature of spacetime and questioning the validity of classical descriptions. In response, advocates of the smooth horizon scenario have proposed alternative mechanisms to resolve the paradox without invoking firewalls. One such approach is black hole complementarity, which suggests that no single observer ever sees both the smooth horizon and the firewall. Instead, the infalling observer experiences a smooth crossing, while an external observer sees information encoded at the horizon. This duality attempts to preserve both quantum mechanics and general relativity, albeit at the cost of a radical departure from classical notions of objective reality. Another smooth horizon model involves the fuzzball proposal discussed earlier, where the horizon is replaced by a quantum state with no interior region. In this view, the classical horizon never truly forms, and there is no firewall per se, but the entire black hole is a quantum object with a complex structure that resolves paradoxes in a nonviolent way. This model preserves the equivalence principle to some degree while still encoding information in the black hole's microstates. Yet the tension between firewall and smooth horizon persists because each theory demands profound revisions to well-established physics. The firewall implies a violent breakdown of spacetime at the horizon, while the smooth horizon demands subtle and intricate quantum structures that evade direct observation. This dilemma highlights the deep incompatibility between quantum theory and general relativity in extreme conditions and underscores the need for a consistent theory of quantum gravity. Experimental verification remains elusive because the event horizon is far beyond the reach of current observational technology. Theoretical tools such as the ADS/CFT correspondence, a realization of the holographic principle, provide powerful frameworks to study these problems by relating gravitational theories in higher dimensional spacetimes to quantum field theories on their boundaries. These dualities have shed light on the entanglement structures underlying horizons and suggest ways to reconcile smooth horizons with quantum unitarity. Moreover, recent developments in quantum information theory have provided new insights into the entanglement properties of black holes and their radiation. Concepts like quantum error correction codes have been proposed to explain how information might be preserved without firewalls, allowing for a smooth horizon consistent with quantum mechanics. These ideas hint at a profound connection between the geometry of spacetime and the structure of quantum information, indicating that the solution to the firewall debate lies at the intersection of these disciplines. The philosophical implications of the firewall controversy are equally profound. It forces physicists to reconsider fundamental principles such as locality, causality, and the nature of observation in quantum gravity. Whether the horizon is smooth or a searing firewall may depend on the observer's frame of reference, challenging classical ideas of an objective reality and suggesting a more relational or observer-dependent universe. In addition to theoretical efforts, numerical simulations of black hole dynamics and analog gravity systems in the laboratory attempt to explore horizon phenomena experimentally. Systems such as ultracold atoms and optical fibers mimic aspects of event horizons and Hawking radiation, offering potential tests of firewall-like effects or smooth horizon predictions. While these analogs do not capture all complexities of astrophysical black holes, they provide valuable insights into horizon physics. The tension between firewall and smooth horizon also feeds into broader debates about the nature of spacetime itself. If firewalls exist, spacetime may be emergent and fragile, breaking down at horizons due to quantum effects. If horizons are smooth, spacetime might be more robust, with quantum gravity effects encoded in subtle, non-local correlations. Each possibility leads to different visions of the quantum gravitational landscape and the ultimate fate of information swallowed by black holes. Ultimately, the firewall versus smooth horizon debate exemplifies the frontier of modern physics, where our most cherished theories confront the unknown. It is a battle of concepts as much as equations, pitting quantum principles against gravitational intuition. Whichever theory prevails, the resolution will transform our understanding of black holes, quantum mechanics, and the nature of reality itself. This controversy also drives the search for a quantum theory of gravity that seamlessly unites general relativity and quantum mechanics. Whether through string theory, loop quantum gravity, or other approaches, the challenge is to explain how event horizons behave at the quantum level, preserving information and respecting fundamental physical laws without contradiction. The outcome of this battle will not only solve one of the greatest paradoxes in physics, but also illuminate the structure of the cosmos at its most extreme and mysterious scales. Black holes, once thought to be simple cosmic sinkholes, now stand as profound gateways to new physics and deeper truths about the universe. Could we use event horizons for time travel? The notion of time travel has long captivated human imagination, featuring prominently in science fiction, philosophy, and theoretical physics. Among the many exotic phenomena predicted by general relativity, black holes and their event horizons have emerged as tantalizing candidates for enabling forms of time travel, albeit with significant caveats. The question, could we use event horizons for time travel? Explores the interface between gravity, space-time geometry, and causality, probing whether the extreme warping around black holes might allow journeys into the past or future. At the core of this idea is the realization that black holes do not merely represent points of no return but also regions where the flow of time itself becomes deeply distorted. Time dilation near the event horizon means that to an outside observer, clocks near the horizon slow dramatically. In theory, an observer falling into a black hole experiences time differently than a distant observer, creating an asymmetry in the perception of past and future. This raises the possibility of traveling forward or backward in time relative to external frames. One avenue toward time travel involves the concept of wormholes, hypothetical bridges or tunnels through space-time connecting distant regions. Some solutions to Einstein's equations, such as the Einstein-Rosen bridge, suggest that black holes might be connected to white holes or other universes via such tunnels. If traversable wormholes existed, and could be stabilized, they might permit shortcuts through space-time, enabling faster-than-light travel or loops in time known as closed time-like curves, CTCs. In this context, event horizons could serve as the boundaries to these time-bending pathways. However, classical black holes, especially the simplest type known as Schwarzschild black holes, do not provide traversable wormholes. Their event horizons are one-way membranes, and anything crossing inward cannot return or communicate back out. The singularity inside acts as a final fate, terminating any path that enters. This limits the prospect of time travel inside classical black holes to a one-way journey into the unknown future. More exotic black holes, such as rotating, Kerr, or charged, Reissner-Nordstrom black holes, possess richer internal structures that theoretically allow for Cauchy horizons, inner boundaries beyond which determinism breaks down, and closed time-like curves might form. Such configurations could in principle allow time loops or backward time travel within the black hole interior. However, these scenarios remain speculative and are likely unstable due to quantum effects or perturbations, which may destroy these delicate structures. Another critical challenge to time travel via event horizons arises from the laws of causality and chronology protection. Theoretical physicist Stephen Hawking proposed the chronology protection conjecture, suggesting that the laws of physics prevent the formation of closed time-like curves in time machines, preserving causal order. Mechanisms such as quantum vacuum fluctuations might destabilize wormholes or prevent their formation, thus safeguarding the universe from paradoxes like the grandfather paradox. Moreover, even if time travel were possible in principle, practical obstacles loom large. The extreme gravitational forces near event horizons would pose unsurvivable hazards to any traveler. Spaghettification and tidal stresses would stretch and crush matter, rendering conventional travel impossible. Beyond physical survival, the energy requirements to stabilize wormholes or manipulate spacetime at such scales are believed to be astronomical, perhaps requiring exotic matter with negative energy density, a substance not yet observed. From a theoretical standpoint, the interplay between event horizons and time travel probes the very nature of time itself. In relativity, time is not an absolute universal flow but a dimension intertwined with space and dependent on the observer's frame of reference. Event horizons exemplify the breakdown of classical intuitions, where time can seemingly freeze or warp dramatically, challenging our notions of past, present, and future. Quantum gravity, still a work in progress, may reshape these ideas further. Some proposals suggest that the event horizon might encode information holographically, implying a deeper quantum structure to spacetime that could alter how causality and time function near black holes. Quantum entanglement and non-local correlations might, in theory, allow phenomena akin to information traveling outside classical causal bounds, though this is not conventional time travel. Additionally, black holes themselves offer a unique perspective on the arrow of time, the asymmetry between past and future. The second law of thermodynamics dictates an increase in entropy over time, and black holes, with their enormous entropy, may define a cosmic direction for time's flow. How this interacts with the possibility of time loops or travel remains an open question, hinting that event horizons could be deeply entwined with time's fundamental nature. The speculative idea of using event horizons as time machines also influences our understanding of quantum measurement and observer-dependent realities. In the black hole complementarity framework, different observers have distinct experiences of spacetime near horizons, complicating any notion of a universal timeline. This relativity of simultaneity at cosmic extremes challenges straightforward concepts of time travel and chronology. Despite these challenges, experimental and observational advances offer indirect ways to explore related phenomena. Precision measurements of gravitational waves from black hole mergers, mapping spacetime near horizons with the Event Horizon Telescope, and laboratory simulations of horizon analogs in quantum fluids and optical systems all contribute pieces to this puzzle. Though direct time travel remains elusive, these studies deepen our grasp of spacetime's fabric and its limits. In philosophical terms, event horizons and their role in time travel spark debates on determinism, free will, and the nature of reality. If time loops or multiple timelines exist, fundamental assumptions about causality and linear history may need revision. Conversely, the universe's apparent resistance to time paradoxes may reveal profound principles ensuring consistent histories and logical coherence. In summary, while the idea of using event horizons for time travel is enthralling and rooted in deep physics, it remains largely theoretical and speculative. Classical black holes do not permit escape or return, and traversable wormholes, if they exist, face daunting theoretical and practical hurdles. Yet the extreme conditions near horizons provide a unique arena for testing ideas about time, causality, and quantum gravity. Whether these cosmic boundaries could ever serve as portals through time continues to challenge and inspire physicists and dreamers alike. Simulated event horizons in quantum experiments. While real black holes lie light years away, beyond direct human reach, physicists have ingeniously recreated analogs of their most enigmatic features in laboratory settings. Among the most intriguing achievements are simulated event horizons, artificial boundaries designed to mimic the behavior of black hole horizons in controlled quantum experiments. These experiments offer valuable insights into the fundamental physics of horizons, quantum field theory, and the interplay between gravity and quantum mechanics, allowing us to probe phenomena otherwise inaccessible. The concept behind simulated event horizons is rooted in the observation that many physical systems exhibit behaviors mathematically analogous to those near black hole horizons. For example, sound waves moving in a fluid flow with varying velocity can encounter a region where the flow's speed exceeds the speed of sound, creating a sonic horizon, a point beyond which sound cannot escape upstream, mirroring the one-way boundary of a black hole event horizon for light. These dumb holes, acoustic black holes, provide experimental platforms for testing ideas about horizon physics in the lab. One of the pioneering experiments was conducted with Bose-Einstein condensates, BECs, ultracold gases cooled to near absolute zero, where atoms behave collectively as a quantum fluid. Researchers generated conditions where phonons, quantized sound waves, experience horizons analogous to event horizons. These setups allowed the study of analog Hawking radiation, the emission of particle pairs at the horizon predicted by Stephen Hawking in 1974 for real black holes. Detecting Hawking radiation from astrophysical black holes remains extremely challenging due to its faintness compared to cosmic background radiation. However, in laboratory analogs, the relative scales and parameters can be engineered to amplify the effect and observe thermal particle emission directly, providing experimental validation of theoretical predictions. Besides acoustic horizons, other simulated event horizons have been created using optical fibers, where variations in refractive index produce horizons for light pulses, and in nonlinear optical materials where the propagation of photons mimics horizon behavior. Experiments with slow light, polaritons, and superfluid helium have also contributed to the growing field of horizon analogs. These quantum experiments reveal fascinating aspects of the quantum vacuum near horizons. For example, the spontaneous creation of particle-antiparticle pairs at the horizon, manifested as phonons or photons in the analog systems, supports the notion that horizons are not mere classical boundaries but dynamic quantum interfaces where vacuum fluctuations are converted into real particles. Moreover, laboratory analogs provide fertile ground for investigating unresolved paradoxes in black hole physics, such as the information paradox and firewall problem. By controlling parameters precisely, scientists explore how information encoded in quantum states behaves when crossing simulated horizons, how entanglement evolves, and how quantum correlations manifest. Importantly, simulated event horizons challenge the strict division between gravity and quantum mechanics by demonstrating that horizon phenomena are not exclusive to astrophysical black holes but arise from more general principles of quantum field theory in curved spacetime. This universality deepens our understanding of how horizons fundamentally alter the vacuum state and particle content perceived by observers. While these experiments do not replicate gravity itself, since the laboratory systems do not curve spacetime as real masses do, they nonetheless provide a powerful window into quantum horizon physics. They test predictions about thermal radiation, quantum decoherence, and entanglement dynamics near boundaries that effectively trap or release information. Simulated horizons also open doors to new technologies, including quantum simulators that exploit horizon physics for information processing, sensors that leverage horizon-induced particle emission for detection, and novel platforms to study non-equilibrium quantum dynamics. As experimental techniques continue to advance, increasing control over temperature, coherence, and interactions in quantum fluids and optical systems promises to simulate more complex horizon scenarios. These may include analogs of rotating black holes, charged horizons, and even dynamical horizons evolving over time, offering closer parallels to astrophysical realities. The interplay between theory and experiment in this field exemplifies the power of analogical reasoning in physics. By finding mathematical similarities across disparate systems, researchers turn seemingly inaccessible cosmic phenomena into tangible laboratory experiences, fostering cross-pollination between quantum optics, condensed matter, and gravitational physics. Furthermore, simulated horizons provide educational tools, making the counterintuitive concepts of black hole physics accessible to students and the public. Visualizations and experimental demonstrations clarify how horizons alter perceptions of space, time, and reality, deepening appreciation for the mysteries of the universe. Nevertheless, it is crucial to recognize the limitations of these analogs. They cannot fully capture the complex, nonlinear interplay of gravity, space-time curvature, and quantum fields present in real black holes. They serve as models or toy universes, valuable for isolating specific effects but not substitutes for complete theories of quantum gravity. Looking ahead, the convergence of simulated event horizons with advances in quantum computing and information theory may uncover new principles governing quantum spacetime, entanglement entropy, and the emergence of classical geometry from quantum substrates. Such research may ultimately inform the quest for a unified theory reconciling Einstein's general relativity with quantum mechanics. In conclusion, simulated event horizons in quantum experiments represent a remarkable frontier where cutting-edge laboratory physics meets profound cosmic questions. By recreating the essence of black hole horizons in tabletop setups, these experiments illuminate the quantum nature of horizons, validate theoretical predictions, and pave pathways toward understanding the deepest mysteries of space, time, and information. The Event Horizon Telescope. The Event Horizon Telescope, often abbreviated as EHT, represents one of the most ambitious and groundbreaking efforts in modern astronomy and astrophysics, a global network of radio telescopes working together to capture images of black holes, objects once considered beyond the reach of direct observation. At the heart of the EHT's mission lies the quest to observe the event horizon itself, the mysterious boundary beyond which nothing, not even light, can escape the gravitational grip of a black hole. This global collaboration is not a single telescope but a virtual Earth-sized observatory created through a technique called Very Long Baseline Interferometry, VLBI. By synchronizing radio dishes scattered across continents, from the Atacama Desert in Chile to the peaks of Hawaii, and from the Spanish island of La Palma to the South Pole, the EHT achieves an angular resolution so fine that it can discern features as small as the event horizon of supermassive black holes millions of light years away. This resolution is akin to spotting a grapefruit on the Moon from Earth. The challenges the EHT faces are immense. Black holes emit no light themselves, making them invisible by conventional means. Instead, the telescope observes the glowing accretion disks of superheated gas and plasma spiraling into the black hole, bent and twisted by its intense gravity. The edge of the black hole, its event horizon, casts a shadow against this luminous backdrop. Capturing this shadow requires overcoming atmospheric interference, extreme distances, and the need for synchronized timing down to fractions of a nanosecond. In April 2019, the EHT collaboration revealed humanity's first ever direct image of a black hole's shadow, specifically, the supermassive black hole at the center of the galaxy M87. This monumental achievement confirmed many theoretical predictions of Einstein's general relativity, showing a bright ring of radiation curving around a dark central shadow, marking the silhouette of the event horizon. This image transformed black holes from theoretical entities into tangible, observed phenomena. The image also revealed unexpected details. The ring was asymmetrical, hinting at relativistic effects such as beaming due to the rotation of the black hole's accretion disk. This provided clues about the black hole's spin, mass, and the dynamics of matter swirling near the event horizon. The data challenged astrophysicists to refine models of black hole environments and the physics of extreme gravity. The EHT's success demonstrated the power of global cooperation and technological innovation. Massive amounts of data collected at each telescope were stored on high-capacity hard drives and transported physically to centralized processing centers, where supercomputers performed complex correlations to synthesize the final image. This process highlighted the fusion of observational astronomy, computer science, and physics. Beyond M87, the EHT aims to image Sagittarius A, the supermassive black hole at the center of our own Milky Way. Although closer, Sagittarius A poses unique challenges due to its smaller size and more dynamic environment, with rapidly fluctuating emissions and variable accretion rates. Capturing its event horizon promises to deepen our understanding of black hole physics in a different mass and activity regime. The EHT also enables tests of fundamental physics. By measuring the shape and size of the shadow, scientists test the predictions of general relativity under extreme gravitational conditions. Any deviations could signal new physics or modifications to gravity theories. This makes the EHT a powerful probe of space-time geometry and the behavior of matter and light near the horizon. Moreover, the telescope helps explore questions about black hole growth and feedback mechanisms in galaxy evolution. Observing how black holes interact with their surroundings via jets and outflows provides insights into their role in shaping cosmic structures. The EHT data integrates with observations across the electromagnetic spectrum to build a holistic picture of black hole ecosystems. The project continues to expand, with plans to add more telescopes to the network and extend observations to shorter wavelengths, increasing resolution and sensitivity. Future campaigns will seek to capture dynamic movies of event horizons, revealing the turbulent physics in real time and tracking changes in accretion and jet formation processes. The implications of the EHT's work ripple beyond astrophysics. By peering into the realms of strong gravity, the telescope challenges our understanding of space, time, and information, bridging observational data with theoretical models. It brings us closer to reconciling quantum mechanics with gravity by providing empirical data on where these frameworks must coexist. In educational and cultural terms, the EHT has ignited public imagination, illustrating the frontiers of science and human curiosity. Its images symbolize the triumph of human ingenuity, perseverance, and the desire to understand the universe's most mysterious objects. As the Event Horizon Telescope continues to push boundaries, it fuels a new era of black hole astronomy, one where the once hidden edges of spacetime are unveiled, where questions about horizons, singularities, and information take on concrete form, and where the interplay between observation and theory deepens our cosmic comprehension. Are event horizons real or illusion? The concept of the event horizon, the ultimate boundary around a black hole beyond which nothing returns, is foundational in astrophysics. Yet, as science advances, the question arises, are event horizons truly, real, physical surfaces in the universe, or are they illusions born from the limits of our current theories and observations? This debate challenges our very understanding of what it means to cross a boundary in spacetime and the nature of reality at the edge of these enigmatic cosmic voids. Classically, an event horizon is defined as a point of no return. According to general relativity, it is a perfectly sharp, well-defined surface enveloping a black hole, marking where the escape velocity equals the speed of light. Once an object crosses this boundary, it is forever trapped by the black hole's gravity. This classical picture treats the event horizon as a mathematically precise, absolute boundary embedded in the fabric of spacetime. However, when quantum effects enter the picture, this neat boundary becomes less clear. Theoretical insights suggest that the horizon might not be a fixed, solid barrier but something more nuanced, perhaps a quantum phenomenon emerging from deeper layers of space-time structure. Some physicists propose that the event horizon could be a fuzzy, or blurred, region where classical and quantum effects blend, making the horizon more of a perceptual or effective boundary rather than a sharp, absolute one. One compelling argument questioning the reality of event horizons comes from the so-called firewall paradox. If event horizons behave as predicted by classical relativity, then according to certain quantum principles, an observer falling into a black hole would experience a searing firewall of high-energy particles at the horizon, contradicting the classical expectation of a smooth passage. This paradox raises the possibility that the classical horizon might not exist as we think, or must be radically reinterpreted. Another perspective emerges from the holographic principle, which posits that all information contained within a volume of space can be represented on its boundary, suggesting the event horizon might be a two-dimensional surface encoding three-dimensional information. In this view, the horizon could be less a physical surface and more a projection or informational boundary. If true, the event horizon's reality becomes a question of perspective, deeply tied to how information and spacetime geometry relate at quantum scales. Moreover, alternative theories such as fuzzballs challenge the classical notion of horizons by replacing them with complex, string-theoretic structures. In fuzzball models, what appears as a horizon in classical theory is actually a tangle of quantum strings and branes, meaning that no traditional event horizon exists. Instead, the black hole is a quantum object with no inside-outside boundary, as conventionally imagined. From the observational standpoint, detecting an event horizon directly is inherently difficult. What we observe, like the EHT's black hole images, are shadows and radiation patterns influenced by gravity but do not directly reveal the horizon's physical nature. This ambiguity fuels speculation whether what we call event horizons are merely apparent boundaries shaped by light bending and extreme gravitational effects, rather than definitive physical barriers. Some researchers argue for the notion of apparent horizons, surfaces that behave like event horizons temporarily but lack the permanence or strict causality attributed to classical horizons. Apparent horizons depend on the observer's frame and local spacetime conditions, further blurring the concept of an absolute event horizon. Additionally, the idea that horizons might be illusory ties into deeper puzzles about the black hole information paradox. Whether information falling into a black hole is truly lost or somehow encoded on or outside the horizon. If information is preserved in subtle correlations accessible beyond the classical horizon, this challenges the horizon's role as an ultimate boundary. Experimental and theoretical progress continues to explore this frontier. Quantum gravity research, combining general relativity and quantum mechanics, strives to reveal whether horizons are fundamental entities or emergent phenomena from more basic building blocks of reality. Advances in quantum simulations, analog black holes, and gravitational wave observations may provide new clues. Ultimately, the question of whether event horizons are real or illusion touches on the limits of human knowledge and the nature of reality itself. It forces physicists to reconsider foundational assumptions, bridging cosmic-scale phenomena with quantum mysteries. In this pursuit, the event horizon serves not only as a boundary in space but as a gateway to new physics and deeper understanding of the universe. Quantum tunneling. Quantum tunneling at the event horizon of a black hole presents one of the most fascinating intersections between quantum mechanics and general relativity, offering a glimpse into processes that challenge our classical understanding of physics. At the heart of this phenomenon lies the idea that particles can escape what would traditionally be considered an inescapable gravitational trap, not by surpassing the speed of light or overcoming the massive pull in a classical sense, but by exploiting the probabilistic nature of quantum mechanics. Quantum tunneling allows particles to tunnel through barriers that classical physics deems impenetrable. When applied to the event horizon, the boundary beyond which nothing can return, this suggests that, under certain conditions, particles might quantum mechanically escape the black hole's grasp. This concept intertwines closely with Hawking radiation, a theoretical prediction that black holes emit radiation due to quantum effects near the event horizon. Hawking's groundbreaking work showed that vacuum fluctuations around the horizon create pairs of virtual particles, where one falls into the black hole while the other escapes, effectively causing the black hole to lose mass over time. Quantum tunneling is the mechanism that allows these escaping particles to pass through the horizon barrier, challenging the classical notion that the event horizon is a perfect one-way membrane. At a more detailed level, quantum tunneling near the horizon involves particles experiencing the event horizon as a potential barrier. Normally, nothing with mass can surmount the gravitational pull beyond this boundary. But quantum physics, with its inherently probabilistic nature, assigns a finite chance that a particle might tunnel through this barrier. This tunneling effect is not limited to particles traditionally thought to escape. It suggests that information and energy might seep out of black holes in subtle ways, potentially providing clues to resolving the information paradox. The mathematics that describe quantum tunneling at the horizon involve complex treatments of curved spacetime and quantum fields in intense gravitational backgrounds. The calculations require merging aspects of quantum field theory with curved spacetime geometry, an endeavor that points toward the need for a unified quantum gravity theory. In practice, these analyses show that the event horizon's strict impermeability softens when quantum effects are taken into account. It becomes a semi-permeable boundary, allowing a trickle of particles and information to leak outward. This phenomenon has profound implications for how we understand black hole thermodynamics and evolution. Quantum tunneling contributes to the gradual evaporation of black holes, making their lifetimes finite rather than eternal. As black holes lose mass through Hawking radiation and tunneling effects, they shrink over immense timescales, eventually disappearing entirely, though the final moments of this process remain shrouded in mystery due to the extreme conditions where classical and quantum theories collide. Quantum tunneling also raises critical questions about causality and locality. How does a particle know to tunnel outward when classical physics forbids escape? The answer lies in quantum non-locality, where particles can instantaneously exhibit correlated behaviors over distances, defying classical intuition. This challenges our common-sense notions of cause and effect and pushes physicists to reconsider the fabric of spacetime itself. Experiments that probe quantum tunneling at black hole horizons remain beyond current technological capabilities, but analog systems and laboratories provide valuable insights. For instance, experiments using ultracold atoms, optical fibers, or Bose-Einstein condensates simulate horizon-like conditions where quantum tunneling effects can be studied. These simulated horizons mimic event horizon physics, allowing researchers to observe analog Hawking radiation and tunneling phenomena, thus opening a window into the quantum processes that might occur around astrophysical black holes. The role of quantum tunneling also ties into debates about the firewall paradox. Some theories propose that an energetic firewall at the event horizon would incinerate anything attempting to cross, contradicting the smooth horizon expected from general relativity. However, quantum tunneling mechanisms suggest a more subtle interplay between information escape and horizon structure, potentially allowing for a less violent transition across the horizon, preserving the principle of equivalence while still accommodating quantum information leakage. Moreover, the quantum tunneling perspective provides a bridge between classical and quantum descriptions of black holes, hinting at how semi-classical approximations might break down near the horizon. It points toward a picture where the event horizon is not an absolute boundary but a quantum interface where classical spacetime gives way to quantum uncertainty and probabilistic behaviors. In the broader quest to unify gravity and quantum mechanics, understanding quantum tunneling at black hole horizons serves as a vital testbed. It encapsulates the challenge of reconciling the smooth, continuous fabric of spacetime with the discrete, probabilistic nature of quantum fields. The phenomenon could hold keys to a future theory of quantum gravity that explains the microstructure of spacetime and the ultimate fate of black holes. Philosophically, quantum tunneling at the event horizon challenges our deepest assumptions about reality. It blurs the lines between inside and outside, past and future, causality and chance. It reveals a universe where boundaries are not absolute but permeable, where the deterministic worldview gives way to a cosmos ruled by probabilities and paradoxes. The future of research in this area promises to be as exciting as the theoretical discoveries themselves. With advancements in observational astronomy, such as improved imaging from the Event Horizon Telescope and gravitational wave detectors, scientists hope to find indirect evidence supporting quantum effects near black holes. The detection of subtle signatures consistent with quantum tunneling or Hawking radiation could revolutionize our understanding of the universe's most enigmatic objects. As we continue to explore the quantum mysteries at the edge of black holes, the notion of quantum tunneling reminds us that reality often defies intuition. It underscores the need for humility in science, recognizing that the cosmos still holds secrets far beyond our current grasp, waiting to be uncovered by future generations of physicists and astronomers. Black hole thermodynamics. Black hole thermodynamics stands as one of the most profound and unexpected intersections between the laws of physics that govern heat, energy, and entropy and the enigmatic properties of black holes, cosmic entities once thought to be utterly simple, defined solely by their mass, charge, and spin. Before the discovery of black hole thermodynamics, black holes were largely considered perfect absorbers of matter and energy, with no apparent temperature or entropy. They were viewed as objects from which nothing could escape, lacking any thermodynamic behavior. However, this perspective shifted dramatically in the 1970s when physicists like Jacob Bekenstein and Stephen Hawking began to explore the surprising thermodynamic properties of black holes, fundamentally transforming our understanding of these cosmic phenomena. At the heart of black hole thermodynamics lies the analogy between the laws of classical thermodynamics and the behavior of black holes, especially as described by their event horizons. This analogy reveals that black holes possess quantities analogous to temperature, entropy, and energy, and that they obey laws remarkably similar to those of thermodynamics. This revolutionary concept was first proposed by Jacob Bekenstein, who suggested that the surface area of a black hole's event horizon is directly proportional to its entropy, a measure of disorder or information content. This idea was radical because entropy had traditionally been associated with the microscopic states of matter, such as molecules in a gas or spins in a magnet. The notion that a black hole, a seemingly simple object defined by just a few macroscopic parameters, could have entropy implied a deep underlying structure. Bekenstein proposed that the entropy of a black hole is proportional to the area of its event horizon divided by the Planck length squared, giving birth to the concept that the horizon encodes information about the black hole's interior. Shortly after Bekenstein's work, Stephen Hawking introduced the concept of black hole radiation, or Hawking radiation, providing a physical temperature to black holes. Hawking showed through quantum field theory calculations that black holes are not entirely black but emit radiation as if they have a temperature inversely proportional to their mass. This emission arises due to quantum effects near the event horizon, where particle-antiparticle pairs spontaneously appear, and one falls into the black hole while the other escapes. This radiation implies that black holes can slowly lose mass and energy, leading to their eventual evaporation over incredibly long timescales. These insights led to the formulation of the 4 laws of black hole thermodynamics, each corresponding to classical thermodynamic laws but applied to black holes. 1. The zeroth law states that the surface gravity of a black hole is constant across its event horizon, analogous to uniform temperature and thermal equilibrium. 2. The first law relates changes in a black hole's mass to changes in its surface area, angular momentum, and electric charge, mirroring the law of energy conservation in thermodynamics. 3. The second law asserts that the total area of all black hole event horizons in a closed system can never decrease, akin to the increase of entropy in classical thermodynamics. This is known as the area theorem and implies that black hole entropy never decreases. 4. The third law posits that it is impossible to reduce the surface gravity to zero by any physical process, paralleling the unattainability of absolute zero temperature. Black hole thermodynamics has deepened our understanding of the nature of gravity and quantum theory, particularly in its implication that information and entropy are fundamental to the structure of spacetime. The idea that a black hole's entropy scales with its horizon area rather than its volume is counterintuitive and suggests that the degrees of freedom describing the black hole might reside on its boundary rather than within its interior, a foundational idea behind the holographic principle. Moreover, this area-entropy relationship challenges traditional notions of locality in physics. It implies that the fundamental description of a black hole, and possibly all of spacetime, is encoded on a two-dimensional surface, giving rise to a holographic view of the universe. This principle has profound implications for quantum gravity, hinting at a universe where information and geometry are deeply intertwined. The thermodynamic properties of black holes also play a crucial role in the ongoing efforts to resolve the black hole information paradox. If black holes evaporate through Hawking radiation, which appears to be purely thermal and random, it raises the question of what happens to the information about the matter that formed the black hole. Does the information disappear, violating quantum mechanics, or is it somehow preserved? Black hole thermodynamics provides the framework within which physicists investigate these puzzles, suggesting that entropy and information are key to unlocking the mysteries of quantum gravity. In practical terms, black hole thermodynamics bridges the gap between the macroscopic and microscopic worlds. It connects the classical picture of spacetime curvature with the quantum behavior of particles and fields. This intersection has driven new theoretical developments, including string theory and loop quantum gravity, where the microscopic degrees of freedom corresponding to black hole entropy can be studied and counted. Additionally, black hole thermodynamics has influenced our understanding of cosmology and the early universe. The principles that govern black hole entropy and temperature are also relevant to cosmological horizons, such as the event horizon of our observable universe. This connection suggests that thermodynamic laws may be universal, applying not only to black holes but also to the fabric of the cosmos itself. One of the most striking outcomes of black hole thermodynamics is the prediction that black holes are not eternal. Over unimaginably long timescales, they radiate energy, lose mass, and ultimately evaporate. This challenges the classical view of black holes as permanent objects and opens questions about the fate of matter and information once a black hole has vanished. Furthermore, the notion that black holes have a temperature and emit radiation implies that they can reach thermal equilibrium with their surroundings, a concept that leads to the idea of black hole heat baths and their interactions with other astrophysical processes. This thermal behavior influences the dynamics of black holes in dense environments, such as galactic centers or merging black holes, affecting gravitational wave emissions and accretion processes. Exploring black hole thermodynamics has also motivated the development of new mathematical tools and conceptual frameworks, including the study of quantum entanglement entropy, which quantifies the information shared between regions separated by horizons. This has provided insights into the quantum structure of spacetime and the entanglement between inside and outside the event horizon. The implications of black hole thermodynamics continue to ripple through theoretical physics, shaping ideas about the unification of forces, the nature of time, and the emergence of spacetime geometry from quantum information. It highlights the deep connections between gravity, quantum mechanics, and statistical mechanics, inviting us to reconsider fundamental questions about the universe. In conclusion, black hole thermodynamics represents a monumental leap in our understanding of the cosmos. It reveals that black holes are far from simple voids but are thermodynamic objects with temperature, entropy, and a rich quantum structure. These discoveries challenge and enrich our view of physics, pointing toward a deeper, more unified theory that reconciles the macroscopic and microscopic realms. As research progresses, black hole thermodynamics will remain a cornerstone in the quest to unravel the ultimate nature of reality. Role of dark matter near the horizon. The role of dark matter near the event horizon of a black hole presents an intriguing and largely uncharted frontier in astrophysics and cosmology. Dark matter, a mysterious form of matter that neither emits nor absorbs light and is detectable only through its gravitational effects, makes up about 27% of the universe's total mass energy content. Despite its pervasive influence on galactic scales and cosmic structure formation, its behavior in the extreme environments near black holes, especially close to the event horizon, remains a subject of active research and profound mystery. To understand dark matter's potential role near a black hole's event horizon, we must first recognize the nature of the environment there. The event horizon marks a boundary beyond which no information or matter can escape, due to the immense gravitational pull of the black hole. In this region, gravity warps spacetime to such an extent that conventional physics breaks down or requires quantum gravitational corrections. The extreme curvature and energy densities challenge our understanding of particle behavior and interactions. Into this exotic landscape, dark matter particles are expected to interact gravitationally, but, unlike normal matter, they do not participate in electromagnetic forces, making their dynamics even more enigmatic. One significant question is how dark matter behaves when it drifts into the gravitational influence of a black hole. Traditional baryonic matter, ordinary matter composed of protons, neutrons, and electrons, forms accretion disks around black holes, heats up due to friction, and emits X-rays and other radiation detectable by astronomers. Dark matter, by contrast, is believed to interact primarily through gravity and possibly weak interactions, so it does not radiate or heat up in the same way. This difference suggests that dark matter could accumulate differently around black holes, perhaps forming a diffuse halo or a spike of increased density very close to the event horizon. Theoretical models predict that dark matter density might sharply increase near a black hole's horizon due to gravitational focusing, creating what is known as a dark matter spike. Such spikes could have implications for the dynamics of black holes and their observable properties. For example, the presence of a dense dark matter spike could alter the black hole's gravitational field subtly, potentially influencing the orbits of nearby stars or the timing of signals emitted close to the horizon. These effects, while incredibly challenging to detect, could provide indirect evidence of dark matter's behavior and its interaction with black holes. Moreover, if dark matter particles can self-annihilate or decay into standard model particles, the enhanced density near the event horizon could produce detectable signals such as gamma rays or neutrinos. This prospect has motivated searches for indirect dark matter detection around supermassive black holes at galactic centers, where both dark matter and black holes coexist in high densities. Although no conclusive signals have been found yet, the possibility remains tantalizing, especially with next-generation observatories' increasing sensitivity. Dark matter's influence near the event horizon also intersects with theoretical ideas about black hole growth and evolution. Black holes grow by accreting matter and merging with other black holes, but could they also accumulate dark matter over time? If so, this process might contribute to the black hole's mass budget in ways not accounted for by luminous matter accretion alone. While the gravitational capture of dark matter by black holes is expected to be less efficient than that of baryonic matter due to the weakly interacting nature of dark matter, its sheer abundance means it could still have a cumulative effect over cosmic timescales. Another fascinating area of exploration is the impact of dark matter on the black hole's event horizon itself. Some theories speculate that dark matter could influence the structure of the horizon, especially if exotic dark matter candidates such as ultralight bosons or axions exist. These particles could form clouds, or condensates, around black holes through a process called superradiance, extracting rotational energy from spinning black holes and potentially modifying the horizon's properties. Such phenomena could produce gravitational waves with characteristic signatures, detectable by observatories like LIGO and Virgo, offering a new window into both dark matter physics and black hole dynamics. The interplay between dark matter and black holes is further complicated when considering the quantum aspects near the horizon. If dark matter interacts via unknown forces or possesses internal structure, quantum effects could manifest near the event horizon in subtle ways. These might influence phenomena such as Hawking radiation or the black hole information paradox, adding new layers of complexity to these enduring puzzles. Furthermore, the presence of dark matter near black holes might have implications for the nature of spacetime itself. Some speculative theories propose that dark matter and dark energy could be manifestations of deeper quantum gravitational effects or emergent phenomena related to the fabric of spacetime. In such scenarios, studying dark matter near event horizons could shed light on the quantum geometry of black holes and their role in the cosmos. From an observational standpoint, probing dark matter near event horizons is extraordinarily challenging. The regions close to black holes are obscured by intense gravitational lensing, high-energy radiation from accretion disks, and extreme relativistic effects. Disentangling signals attributable to dark matter from those caused by ordinary matter and complex astrophysical processes requires precise modeling and innovative detection techniques. Advancements in technology, such as the Event Horizon Telescope's imaging of black hole shadows, high-energy gamma-ray telescopes, and gravitational wave detectors, offer promising avenues to investigate the dark matter-black hole connection. By analyzing the motion of stars around black holes, searching for indirect annihilation signals, and detecting potential gravitational wave signatures of dark matter interactions, scientists hope to uncover clues about dark matter's presence and influence near these cosmic giants. The role of dark matter near a black hole's event horizon is not just a question of astrophysics, but also a profound inquiry into the fundamental nature of matter, gravity, and the universe. Understanding this interplay could illuminate the hidden side of the cosmos, revealing new physics beyond the standard model and enhancing our grasp of black holes as laboratories for extreme conditions. In summary, while much remains speculative and under active investigation, dark matter near the event horizon represents a fascinating frontier. Its gravitational dance with black holes could subtly shape the properties and evolution of these enigmatic objects, influence observable phenomena, and provide critical insights into the universe's darkest mysteries. As research continues and observational capabilities improve, the veil over dark matter's role near black holes will gradually lift, bringing us closer to answering some of the most profound questions in modern physics and cosmology. Effects of black holes' spin on the event horizon. The spin of a black hole, also referred to as its angular momentum, plays a profound and transformative role in shaping not only the black hole's structure but also the very nature of its event horizon. Unlike non-rotating, or Schwarzschild, black holes which are perfectly spherical, rotating black holes, described by the Kerr solution to Einstein's field equations, exhibit a much more dynamic and complex geometry. The event horizon of a spinning black hole is oblate, meaning it is flattened at the poles and bulging at the equator due to the effects of rotation. This deformation is not merely a geometric curiosity, it has dramatic consequences for the behavior of spacetime in the vicinity of the black hole. The rotation of a black hole gives rise to a region outside the event horizon known as the ergosphere. This region is where the effects of frame dragging become unavoidable. Frame dragging, a prediction of general relativity, is the phenomenon where spacetime itself is twisted and dragged around by the rotating mass of the black hole. Within the ergosphere, any object, including light, must co-rotate with the black hole. It is impossible to remain stationary in this zone because spacetime is being pulled around faster than any external force can counteract. The boundary of the ergosphere touches the event horizon at the poles and extends outward at the equator, creating a shape that resembles an elongated spheroid. The ergosphere is not just a passive region, it has theoretical implications for energy extraction from a rotating black hole. One such mechanism is the Penrose process, wherein a particle entering the ergosphere can split into two, with one fragment falling into the event horizon and the other escaping with more energy than the original particle. The excess energy comes from the black hole's rotation, allowing, in theory, the gradual slowing of the black hole while generating energy. This process has implications for high-energy astrophysics, particularly for understanding the power behind relativistic jets and energetic phenomena observed around supermassive black holes. The spin rate of a black hole is quantified by a dimensionless spin parameter, usually denoted as a, which ranges from 0, non-rotating, to 1, maximally rotating. As the spin parameter increases, the radius of the event horizon decreases, bringing the inner edge of the black hole closer to the central singularity. In a maximally spinning Kerr black hole, the event horizon is at its smallest possible size for a given mass, and the ergosphere becomes much more pronounced. This contraction of the event horizon alters the gravitational well experienced by matter falling into the black hole and significantly affects accretion dynamics. Black hole spin also affects the innermost stable circular orbit, ISCO, around the black hole, the closest distance at which matter can stably orbit without spiraling inward. For non-rotating black holes, the ISCO is located at 3 times the Schwarzschild radius. However, for a maximally spinning black hole, the ISCO can lie much closer, at just the radius of the event horizon. This proximity allows accretion disks to radiate more energy, as matter falling into a fast-spinning black hole can convert more of its gravitational energy into radiation before crossing the event horizon. This mechanism may help explain the tremendous luminosity of quasars and active galactic nuclei. Interestingly, spin-induced frame dragging leads to what is known as length-stirring precession, in which the orbit of matter or even the spin axis of a nearby object slowly rotates due to the twisting of spacetime. This effect has been confirmed through satellite measurements around Earth but becomes exponentially more powerful near rapidly spinning black holes. In these environments, length-stirring precession can twist and warp the inner parts of accretion disks, possibly accounting for observed variability in the emitted X-ray and gamma-ray spectra from certain black hole systems. From a thermodynamic perspective, black hole spin also influences temperature and entropy. According to the laws of black hole thermodynamics, the surface area of the event horizon corresponds to the entropy of the black hole, and this surface area decreases as the black hole spins faster. In other words, a rotating black hole of a given mass will have less surface area, and hence lower entropy, than a non-rotating one. This difference has implications for the statistical understanding of black hole microstates, particularly in string theory and holographic models that attempt to count the quantum states associated with black hole entropy. In terms of observational consequences, the spin of a black hole leaves clear fingerprints on the light escaping from the environment around the event horizon. Due to the Doppler effect and gravitational lensing, light emitted from the inner edge of an accretion disk around a rapidly rotating black hole is asymmetrically shifted, creating broadened and skewed spectral lines. This effect allows astronomers to estimate the spin of astrophysical black holes by analyzing the X-ray emissions from iron lines and other spectral features. Observations using telescopes like Chandra, NuStar, and XMM Newton have helped catalog the spin rates of several black holes, revealing that many of them rotate at near maximal rates. The effect of spin becomes even more important in the context of merging black holes. When two black holes collide and merge, events now regularly observed through gravitational waves, their spins interact in complex ways. Depending on the alignment and magnitude of their spins, the resulting black hole can receive a powerful kick, potentially ejecting it from its host galaxy. Spin also affects the waveform of the emitted gravitational radiation, providing crucial clues for interpreting LIGO and Virgo data and modeling the astrophysical population of black holes. Spin may also influence theoretical explorations of black hole interiors and horizons. Some proposals suggest that spinning black holes could harbor inner horizons or even avoid singularities altogether under certain quantum gravity models. The possibility of traversable wormholes or exotic geometries emerging from rotating black holes, particularly in solutions beyond general relativity, remains an area of vibrant theoretical speculation. There's also growing interest in the role of black hole spin in jet formation. Observations have shown that rapidly spinning black holes often produce highly collimated, relativistic jets of plasma extending thousands of light-years into space. The Blandford's-Nagic mechanism is one model proposing that spin energy is extracted via magnetic fields threading the event horizon, powering these jets. This phenomenon connects the microscopic physics of the event horizon to large-scale structures that influence galaxy formation. Spin also plays a role in black hole evaporation via Hawking radiation. Although the temperature of Hawking radiation is extremely low for astrophysical black holes, a spinning black hole may radiate more rapidly due to superradiant effects, especially for particles with angular momentum. This theoretical nuance suggests that rotation could accelerate black hole evaporation under specific conditions, particularly in scenarios involving primordial black holes or modified theories of gravity. In the quantum realm, spin introduces challenges for modeling the horizon as a coherent boundary in spacetime. Questions arise about how angular momentum is encoded in the entanglement patterns across the horizon and how this might influence the information paradox. Some holographic theories suggest that black hole spin alters the correspondence between boundary field theories and the geometry of the black hole interior, hinting at deeper layers of reality yet to be fully understood. Finally, the interaction between spin and quantum fields near the horizon could provide a testing ground for unifying general relativity and quantum mechanics. Phenomena such as black hole superradiance, spin-induced particle production, and modified commutation relations near rapidly spinning horizons all point to the rich complexity introduced by angular momentum. These interactions may hold the key to new insights into quantum gravity, potentially unlocking the secrets that lie hidden behind the veil of the event horizon. Exotic particles created at the edge. At the very edge of a black hole, near the event horizon, the quantum vacuum becomes an arena of intense activity. According to quantum field theory in curved spacetime, the vacuum is not empty but filled with fluctuating virtual particles constantly appearing and annihilating in pairs. Near the event horizon, these pairs are influenced by the black hole's immense gravity. In some cases, one particle of the pair may fall into the black hole while the other escapes. This process lies at the heart of Hawking radiation, and it also opens up the possibility for the creation of exotic particles, ones that are rare, high energy, or may not exist under normal terrestrial conditions. The powerful tidal forces and extreme gravitational gradients at the horizon create a unique condition known as a gravitational particle factory. In this environment, the virtual particles that briefly flicker into existence may gain enough energy from the black hole's gravitational field to become real. This process is not only limited to the generation of photons or electrons. Under sufficiently energetic conditions, it could also create more massive or hypothetical particles, such as axions, gravitinos, or dark matter candidates that have yet to be confirmed in particle accelerators. One class of exotic particles theorized to emerge near black hole horizons are gravitons, hypothetical quantum particles that would mediate the force of gravity. Although gravitons remain unobserved, black holes offer a natural laboratory where spacetime curvature is extreme enough to potentially give rise to them. If quantum gravity is correct, especially in string theory or loop quantum gravity, the edge of a black hole may radiate not just Hawking particles, but gravitons as well, carrying away tiny packets of gravitational energy into the universe. Supersymmetry, a proposed extension of the Standard Model, predicts the existence of superpartners for every known particle, neutralinos, selectrons, quarks, and more. These particles are thought to be too massive or unstable to appear in current collider experiments. Yet the extreme energy densities at the event horizon may briefly allow such superpartners to manifest. If so, black holes could be natural portals into the supersymmetric sector of physics, producing particles that decay into gamma rays, neutrinos, or other detectable signatures in the cosmos. Quantum fluctuations near the event horizon also offer a setting for the production of axions, hypothetical, low-mass particles originally proposed to solve the strong CP problem in quantum chromodynamics. Axions are also strong dark matter candidates. Certain models suggest that axions could be generated in the presence of intense electromagnetic fields, especially if a black hole is spinning rapidly. These axions might interact weakly with ordinary matter but could decay into detectable photons under certain circumstances, leaving imprints in the electromagnetic spectrum near black holes. Another speculative product of the event horizon's extremity is the creation of mini black holes themselves. In scenarios involving extra dimensions, as posited by some versions of string theory, gravity becomes stronger at small scales. The formation of tiny, short-lived black holes from particle collisions near the event horizon may then be possible. These micro-black holes would evaporate quickly via Hawking radiation, potentially releasing a cascade of high-energy particles that could inform us about extra-dimensional physics. The strong magnetic fields in the vicinity of a rotating black hole can also play a role in particle creation. Through processes such as magnetic reconnection and synchrotron acceleration, particles trapped in magnetic field lines may be energized to near-light speeds. These interactions can give rise to exotic plasma states composed of particles and antiparticles. The extreme environment might allow quark-gluon plasma, usually only achievable in high-energy collider experiments, to briefly exist near the horizon before cooling and fragmenting into hadrons. Near the event horizon, neutrino production also becomes highly significant. These ghost-like particles can traverse dense regions of space without interacting, making them excellent messengers of high-energy astrophysical events. When matter accretes onto a black hole, the intense heating and compression of particles can lead to the copious creation of neutrinos. In speculative models, even sterile neutrinos, an uncharged and weakly interacting form of neutrino, may be generated and escape, offering clues to beyond standard model physics. Black holes may also trigger the Unruh effect, a phenomenon where accelerating observers detect a warm bath of particles in what others perceive as a vacuum. Near the event horizon, where the relative acceleration between frames becomes extreme, virtual particles may become real to an outside observer. This dynamic has led some theorists to explore whether black holes act as amplifiers of vacuum fluctuations, converting quantum noise into real, observable particles. Another potential product of black hole edges are tachyons, hypothetical particles that always travel faster than light. While not part of mainstream physics, tachyons are still explored in theoretical contexts. Some interpretations of string theory and brane cosmology suggest that tachyonic fields may condense near gravitational boundaries, contributing to instabilities or transitions in spacetime. Though no evidence of tachyons has been found, the horizon may be one of the few environments where their effects, if real, could manifest. In some variants of quantum field theory, particles could tunnel into different vacuum states, false or true vacuums. The region near a black hole's event horizon may catalyze such transitions due to its energy density and spacetime curvature. If this occurs, it might produce domain walls or bubble universes, each containing different physical constants, or even separate timelines. These speculative particles and structures belong to the frontier of quantum cosmology, where the physics of black holes and the early universe overlap. Exotic bosons and scalar particles also come into play. Some models predict that massive scalar fields can clump around black holes, forming quasi-stable structures called boson clouds. These clouds may radiate gravitational waves at specific frequencies, forming unique signals that could be detected by observatories like LIGO or LISA. The existence of such clouds hinges on the particles being extremely light and weakly interacting, properties common to many dark matter candidates. One of the most enigmatic products of the horizon could be the creation of virtual wormholes. While speculative, some quantum gravity approaches suggest that spacetime foam, a hypothesized structure at the Planck-scale, could briefly form and dissolve microscopic wormholes. These structures might allow particles or information to take shortcuts through space and time. While currently undetectable, they may influence the black hole's quantum behavior, potentially solving problems like information loss or entanglement monogamy. Additionally, strangelets, hypothetical particles made of strange quarks, could arise in the extreme densities near the event horizon. These ultra-dense chunks of matter may be stable under conditions found only near black holes. If strangelets exist, they could represent an entirely new form of matter, potentially contributing to the makeup of neutron stars or black hole interiors. The formation of such particles remains theoretical but adds to the inventory of what might emerge near the gravitational abyss. In higher dimensional theories, the edge of a black hole may intersect with branes, hypersurfaces that carry different physical properties. The interaction between a black hole's horizon and a hidden brane could produce exotic fields or particles with no analog in our observable universe. These particles might decay quickly or vanish into extra dimensions, but they could also leave faint signatures in the form of gravitational anomalies or unexplained emissions. Even within established physics, the region near a black hole pushes particles to their limits. Under certain gravitational and magnetic conditions, particles may enter highly excited quantum states or interact in combinations that do not normally occur in nature. These interactions, though brief, provide clues about the unification of forces, the stability of matter, and the quantum structure of spacetime itself. Ultimately, the creation of exotic particles at the edge of a black hole is not merely a side effect of its gravity. It may be a vital process for understanding the universe at its most fundamental level. These particles, if observed or inferred through indirect means, would act as messengers from the brink of the abyss, carrying information about physics beyond our current models. The event horizon, far from being a silent boundary, could be one of the most active and revealing laboratories in the cosmos. Influence of magnetic fields at the horizon. The influence of magnetic fields at the event horizon of a black hole is profound, often shaping the behavior of matter and energy in unexpected ways. While black holes themselves are not thought to have inherent magnetic fields, since they have no hair, as the famous theorem suggests, they can interact with magnetic fields generated by the charged particles spiraling around them. These fields, when trapped in the accretion disk or dragged by the rotating spacetime of the black hole, can become amplified to extreme levels, producing effects observable across vast cosmic distances. As matter falls into a black hole, it typically forms an accretion disk, a swirling, flattened structure composed of plasma and highly ionized gas. Within this turbulent environment, magnetic fields are twisted and wound by the rotation of the disk and, in the case of a spinning, black hole, by the dragging of spacetime itself, a relativistic phenomenon known as frame dragging. These magnetic fields can reach intensities billions of times greater than those found on Earth, creating zones of immense electromagnetic stress at the very edge of the event horizon. One of the most striking consequences of these magnetic fields is their role in jet formation. In many active galactic nuclei and quasars, black holes produce powerful relativistic jets that blast matter outwards at nearly the speed of light. These jets are believed to be launched and collimated by magnetic fields near the horizon. In particular, the Blandford's-Nagic mechanism proposes that energy can be extracted from a spinning black hole via magnetic fields, which act as a conduit between the black hole's rotational energy and the escaping plasma. At the event horizon, the interplay between gravity and magnetism reaches a delicate balance. The gravitational pull tries to drag everything inward, while the magnetic fields can push particles along field lines that extend outward from the disk. In this dynamic zone, particles may be accelerated to extreme energies, creating intense radiation and complex interactions. Magnetic reconnection, where field lines break and reconnect, releasing explosive energy, becomes highly likely in this environment, powering sudden bursts of X-rays and gamma rays. In some simulations, magnetic fields near the event horizon are seen to form magnetically arrested disks, MADs. In this scenario, the accumulation of magnetic flux near the black hole becomes so strong that it chokes the inflow of gas. The result is a system dominated by magnetic pressure rather than kinetic or thermal energy, which alters the behavior of the accretion disk, regulates the feeding of the black hole, and enhances jet power. The existence of MADs would explain why some black holes are radio loud, while others remain quiet, despite similar feeding rates. The alignment and structure of magnetic fields near the horizon are not static. General relativistic magnetohydrodynamic (GRMHD) simulations show that magnetic field lines can be twisted into helical shapes as they plunge toward the black hole. These twisted structures may reconnect or break, leading to violent ejections of energy. The topology of the field, whether poloidal, vertical, or toroidal, circular, can determine the stability of the disk and the characteristics of any outflows or jets. Magnetic fields also influence the polarization of light emitted near the black hole. As photons travel through the magnetized plasma near the horizon, their polarization is altered by the Faraday effect. By observing these polarized signals, astronomers can infer the geometry and strength of the magnetic field. In fact, the Event Horizon Telescope's image of the black hole in M87 was not just a shadow. Follow-up studies revealed the polarization structure of the light, offering a glimpse into the magnetic scaffolding around the black hole. Another critical role played by magnetic fields is in the heating of the accretion disk. As charged particles spiral along magnetic field lines, they radiate energy via synchrotron emission. This radiation heats the surrounding plasma, increases ionization levels, and contributes to the overall luminosity of the system. This self-sustaining cycle, where magnetic fields accelerate particles that in turn radiate and heat the disk, maintains the high-energy environment necessary for the continued evolution of the accretion structure. In rotating black holes, magnetic fields can become entangled with the ergosphere, the region just outside the event horizon where spacetime is dragged faster than the speed of light, relative to a distant observer. Within the ergosphere, magnetic field lines may become wound tighter and tighter, creating tension that can launch powerful jets. This phenomenon enhances the efficiency of energy extraction, allowing some systems to convert up to 30% of infalling mass into radiative or kinetic energy, a figure far surpassing nuclear fusion. Even beyond jet production, magnetic fields at the horizon can regulate the growth of the black hole itself. By influencing the angular momentum of infalling matter, magnetic torques can determine how efficiently material spirals inward. In some models, magnetic braking slows down the disk, increasing its density and making it more unstable. These instabilities can lead to sudden infall events, feeding frenzies that light up the surrounding galaxy with a flare of high-energy emission. Quantum electrodynamic effects may also emerge in the presence of strong magnetic fields near the horizon. When magnetic fields approach the critical Schwinger limit, where the vacuum becomes unstable, electron-positron pairs can be spontaneously created. This process, known as vacuum breakdown, can result in bursts of particle-antiparticle plasma that feed back into the disk and influence jet dynamics. Although still speculative, such conditions might exist in magnetized black holes known as magnetars, or in black holes embedded in particularly energetic accretion flows. Magnetic fields may also assist in solving the black hole information paradox. Some recent theoretical approaches suggest that magnetic fields could preserve quantum correlations or create subtle memory imprints in the surrounding plasma, potentially storing information about what falls into the black hole. These correlations, though faint, might be imprinted in the Hawking radiation or in the behavior of entangled particles near the event horizon. In the context of loop quantum gravity, magnetic fields near the horizon might interact with quantized structures of spacetime. Rather than treating the horizon as a smooth surface, loop models propose it is composed of discrete area quanta. These quanta could resonate with magnetic fluctuations, producing patterns or echoes that encode information about the black hole's interior or its quantum history. On cosmic scales, magnetic fields carried by black holes may seed large-scale magnetism in galaxies and intergalactic space. As jets expand and push against the interstellar medium, they carry magnetic fields into the surrounding environment. Over time, this contributes to the magnetization of entire galaxy clusters, influencing star formation, galactic rotation, and the propagation of cosmic rays. The black hole, in this view, becomes a cosmic dynamo, transmitting magnetic structure far beyond its own vicinity. One of the most puzzling aspects of black hole magnetic fields is their potential to influence time itself. As general relativity suggests, strong gravitational and electromagnetic fields can warp time differently for different observers. In regions of intense magnetism near the horizon, this warping may be even more complex, causing clock rates to differ dramatically and potentially creating observational signatures that reveal more about the fabric of spacetime. Finally, magnetic fields may play a key role in transitions between black hole states. Just as neutron stars can collapse into black holes or merge to create new configurations, the magnetic structure of the infalling matter may dictate what kind of black hole emerges. It could also influence whether the final remnant is stable, spins rapidly, or emits gravitational waves strong enough to be detected across the cosmos. The event horizon is far from a silent void. It is a seething frontier shaped by intense magnetism, quantum fluctuations, and the curvature of spacetime itself. Magnetic fields, though invisible, thread through this chaos, guiding particles, regulating flows, and perhaps whispering the secrets of quantum gravity. The relationship between wormholes and event horizons. The relationship between wormholes and event horizons is a subject of deep fascination and speculation in theoretical physics, as both concepts arise from Einstein's general theory of relativity but suggest vastly different cosmic behaviors. While event horizons are boundaries from which nothing can escape, wormholes are often conceived as shortcuts through spacetime, potentially connecting distant regions of the universe, or even different universes entirely. Understanding how these two phenomena intersect, diverge, or perhaps coexist requires exploring the very structure of spacetime itself. At first glance, wormholes and black holes seem to belong to opposing categories, one as a one-way gate into oblivion, the other as a hypothetical tunnel offering passage through space and time. However, mathematically, the first solutions to Einstein's equations that hinted at wormhole-like structures were closely tied to black holes. The Schwarzschild solution, which describes a non-rotating black hole, also contains a second asymptotically flat region beyond the event horizon, suggesting the theoretical existence of a bridge, or throat. This structure is known as the Einstein-Rosen bridge. The Einstein-Rosen bridge is often considered the earliest model of a wormhole, but it is highly unstable. The bridge pinches off too quickly for anything, even light, to pass through. Essentially, it is a fleeting mathematical artifact in the geometry of a black hole that collapses before traversal can occur. In this way, the Einstein-Rosen bridge connects wormholes directly to event horizons, but only as a non-traversable feature embedded in the geometry of a black hole. In more speculative theories, stable and traversable wormholes could exist under very specific conditions, most notably, with the presence of exotic matter. This type of matter, which would violate the known energy conditions of classical physics, could counteract the intense gravitational collapse near an event horizon. Theoretically, exotic matter could keep a wormhole throat open long enough for particles, information, or even spacecraft to pass through. Such wormholes would not necessarily have event horizons in the traditional sense, since they wouldn't trap matter permanently. Nonetheless, some models propose wormholes with event horizon-like surfaces. In these cases, the geometry near the wormhole throat mimics that of a black hole, and the structure may exhibit similar time dilation and redshift effects. However, unlike black holes, these wormholes might allow for two-way travel, at least in theory. The boundary between being trapped inside and being able to escape becomes blurred in these models, challenging the classical understanding of horizons. The most intriguing connections between wormholes and event horizons come from quantum gravity and holography. The ER equals EPR conjecture, proposed by physicists Leonard Susskind and Juan Meldacena, posits that entangled particles, EPR pairs, might be connected by non-traversable wormholes, ER bridges. This radical idea suggests that spacetime connectivity and quantum entanglement are fundamentally linked. In this view, even the interior of a black hole could be quantum entangled with the outside universe via microscopic wormhole-like structures. This concept has led to the idea that wormholes might be involved in resolving the black hole information paradox. If information is not lost behind the event horizon, it may be because the black hole's interior is subtly connected to the exterior via quantum wormholes. These invisible bridges could serve as conduits for entangled information, preserving unitarity and maintaining the consistency of quantum theory even in the presence of event horizons. Moreover, rotating or charged black holes offer even more exotic possibilities. The Kerr and Reissner-Nordstrom solutions to Einstein's equations allow for inner and outer horizons, and their maximal extensions suggest complex spacetime geometries that resemble wormhole-like tunnels. While these solutions are not stable under realistic astrophysical conditions, they demonstrate that the mathematical language of general relativity naturally blends the concepts of horizons and tunnels. In certain brainworld and string theory scenarios, wormholes may arise not in our 4D spacetime, but in higher dimensional frameworks. In these models, black holes in our observable universe might actually be projections or intersections of more complex higher dimensional wormhole structures. In such settings, the event horizon we observe could be only a part of a greater multidimensional topology, where passage through the throat of a wormhole corresponds to movement along hidden spatial dimensions. Quantum tunneling near the event horizon also raises interesting questions about wormholes. If particles can quantum tunnel through the horizon, as in Hawking radiation, could similar quantum effects allow the creation or stabilization of microscopic wormholes? Some speculative models suggest that at the Planck scale, spacetime may be a frothy, fluctuating foam filled with transient wormholes. These quantum wormholes might constantly form and collapse near event horizons, influencing the thermodynamics and entropy of the black hole. The concept of time travel further complicates the relationship between wormholes and event horizons. A traversable wormhole could, under certain conditions, allow for time loops and causal violations, challenges that are normally blocked by the event horizon of a black hole. While black holes obey the cosmic censorship conjecture, hiding singularities behind horizons, wormholes could potentially expose regions of spacetime that defy causality, requiring novel constraints or unknown physics to resolve the paradoxes they introduce. Some physicists propose that the interior of a black hole may not end in a singularity at all, but rather connect to another universe or another region of our own through a wormhole. These hypothetical white holes would be the mirror image of black holes, regions from which matter and information could only emerge. Though speculative, this idea leads to a symmetrical view of spacetime where wormholes act as bridges between the black and white hole pair, linking collapse with expansion. There are also intriguing similarities in the way that time behaves near event horizons and wormholes. Near a horizon, time appears to slow down drastically for an outside observer. Likewise, the geometry near the throat of a wormhole can lead to extreme time dilation, particularly if the ends of the wormhole are moving differently or embedded in different gravitational environments. This temporal warping might enable not just space travel, but also time travel under certain conditions. Holographic dualities further deepen the relationship. In the ADS/CFT correspondence, black holes in a bulk de Sitter, ADS, space can have dual descriptions in a lower-dimensional conformal field theory. Some interpretations suggest that wormholes, too, have such duals, and that horizons and throats may be holographically encoded in the quantum states of boundary theories. This brings a unifying vision where the geometry of the universe, and the bridges and boundaries it contains, arises from deeper informational principles. In essence, the event horizon and the wormhole are not isolated concepts, but part of a broader spectrum of spacetime behavior. They represent different facets of how gravity and geometry interact at extreme scales. While the event horizon defines the boundary of no return, wormholes suggest the tantalizing possibility that escape and passage are still somehow possible, at least in the realm of theory. In many ways, wormholes represent the cosmic antithesis to black holes. One devours, the other connects. Yet both require us to grapple with the limits of our understanding, to reconcile relativity with quantum mechanics, and to envision a universe where space and time are far more malleable than they appear. The intersection of wormholes and event horizons invites us to imagine that the very things we once thought were barriers, walls against the known, might actually be doors, waiting to be unlocked by the physics of the future. Entanglement across the horizon. Entanglement across the horizon represents one of the most profound and mysterious concepts in modern theoretical physics. At the intersection of quantum mechanics and general relativity, it suggests that particles on opposite sides of an event horizon, one trapped within a black hole and the other outside, can remain deeply connected through quantum entanglement. This phenomenon challenges traditional notions of locality and separability and plays a critical role in resolving the paradoxes surrounding black holes, particularly those concerning information loss. In standard quantum theory, entanglement is a condition where two or more particles share a joint quantum state, such that the measurement of one instantly determines the state of the other, no matter how far apart they are in space. When one of these particles falls into a black hole, crossing the event horizon, the question arises, what happens to their entanglement? If the black hole severs this connection, it would contradict quantum theory's requirement for unitary evolution. But if the entanglement is preserved, it implies that some form of non-local connection extends across the horizon. Hawking radiation is a pivotal aspect of this puzzle. According to Stephen Hawking's groundbreaking theory, black holes are not completely black but emit radiation due to quantum effects near the event horizon. This radiation arises from entangled particle pairs spontaneously forming near the horizon. One particle escapes to infinity as radiation, while the other falls into the black hole. The two remain entangled, even as they are forever separated by the horizon. This leads to a troubling scenario. As more radiation escapes, entangled with particles that fall in, the entanglement entropy outside increases. But eventually, the black hole evaporates. This sets the stage for the infamous black hole information paradox. If the black hole disappears entirely and the interior particle is lost, what becomes of the entangled partner outside? Quantum mechanics forbids this kind of information destruction. Either quantum mechanics needs revision, or black holes must somehow preserve and eventually return the information encoded in the entanglement, even across an event horizon. This mystery has pushed physicists toward bold new ideas, including holography, quantum gravity, and even the restructuring of spacetime itself. One resolution to this paradox is the complementarity hypothesis, which suggests that no single observer can access both sides of the entanglement simultaneously. To an outside observer, information appears to be radiated out via Hawking radiation, while from the viewpoint of someone falling in, the information is absorbed. This duality would preserve unitarity and avoid contradictions. But deeper exploration has revealed that such complementarity may not be sufficient to explain all aspects of the paradox, especially as black holes age and their entropy approaches a maximum. The concept of entanglement islands offers a more recent and compelling resolution. Proposed through advancements in the holographic principle and quantum extremal surfaces, this idea posits that certain regions inside the black hole can be included in the calculation of entanglement entropy of the radiation. Remarkably, this implies that the information seemingly hidden behind the horizon is actually encoded in the radiation outside. The inside and outside are no longer independent systems but form a unified, entangled whole. This radical conclusion is supported by calculations in simplified gravitational systems, especially in two-dimensional models of black holes known as Jakob-Teitelbaum gravity. In these models, the entropy of the Hawking radiation initially increases but eventually reaches a plateau and declines, a behavior consistent with the so-called Page curve. This curve reflects the restoration of information and suggests that the entanglement across the horizon is not lost but redistributed. These discoveries hint at a deeper truth. Space-time itself may emerge from entanglement. In certain theories of quantum gravity, the geometry of space and the connectivity of regions may be defined by patterns of quantum entanglement. In this picture, the event horizon is not a fundamental barrier but a geometric manifestation of an underlying quantum entangled state. The entanglement wedge and bulk reconstruction concepts in holography support this idea, showing how information inside a black hole might be decoded from the entangled radiation outside. The ER equals EPR conjecture brings this to its most speculative frontier. Proposed by Meldesena and Susskind, it suggests that every entangled pair, EPR, is connected by a non-traversable wormhole, Einstein-Rosen bridge, or ER. If true, it would mean that entanglement is not just a spooky connection but a literal thread of space-time geometry linking distant regions, even across an event horizon. The black hole interior and its Hawking radiation may then be connected by a vast network of tiny wormholes, maintaining information conservation through geometric structure. Another implication of entanglement across the horizon is its effect on firewalls. In 2012, the AMPS paradox, named after Almhiri, Marov, Polchinski, and Sully, suggested that preserving both unitarity and the smoothness of spacetime at the horizon is impossible. They argued that the entangled Hawking particles outside the black hole must be monogamous. They cannot be entangled with more than one system. Thus, if early Hawking radiation is entangled with later emissions to preserve unitarity, the entanglement between a Hawking particle and its infalling partner must break, creating a high-energy firewall at the horizon. This firewall would incinerate anything falling in, violating the equivalence principle. This created a crisis: either we abandon unitarity, allow firewalls, or rethink the structure of entanglement. Several proposed solutions reject the firewall by suggesting more complex entanglement patterns or modifying the structure of the horizon itself. For instance, in fuzzball theories from string theory, the black hole is not a singularity surrounded by empty space but a highly complex, quantum state with no traditional horizon. In such a model, entanglement is distributed across this complex structure in a way that avoids paradoxes. Even outside theoretical physics, entanglement across the horizon offers intriguing analogies. In condensed matter systems, researchers study entanglement entropy as a tool to probe phase transitions and quantum critical behavior. These studies mirror the way physicists attempt to understand black holes as thermodynamic systems with entropic surfaces. The idea that entanglement defines the boundary, whether in a lab or in the cosmos, hints at a universal principle underlying all of nature. Quantum field theory in curved spacetime reinforces this connection. Fields near the event horizon must be described in terms of modes that are entangled across the boundary. The vacuum state itself, what we normally think of as empty space, is full of entanglement between inside and outside. The very presence of a horizon splits these modes, and the vacuum becomes a thermal bath of particles to an outside observer. Thus, the event horizon is both a physical and informational boundary shaped by entanglement. Furthermore, studies in quantum error correction and tensor networks show how entangled systems can be used to encode information in redundant ways. These models are being applied to understand how black hole interiors might be constructed and protected. If information that falls into a black hole is encoded across many entangled qubits in Hawking radiation, it might be recoverable via advanced decoding techniques, offering a practical, if theoretical, path to resolving the information paradox. Ultimately, entanglement across the event horizon blurs the line between separation and unity. In our classical picture, the horizon divides space into disconnected regions. But quantum entanglement reveals an invisible bridge, a thread that maintains coherence, even when space itself seems to have been split. This insight could be the key to unifying quantum mechanics and gravity. In conclusion, entanglement across the horizon is more than a theoretical curiosity. It is a window into the deep structure of space-time, a guiding principle in the quest for quantum gravity, and possibly the glue that binds the universe together. From resolving paradoxes to redefining geometry itself, entanglement remains at the heart of our most profound questions about reality. Impact of accretion disks on horizon dynamics. Accretion disks, the luminous structures formed by matter spiraling into a black hole, are not mere side effects of gravitational pull. They are active participants in the evolution of black holes themselves. The dynamics of the event horizon are intricately influenced by the behavior of the accretion disk, both through the matter it supplies and the intense fields it generates. Far from being a passive boundary, the event horizon is constantly shaped and reshaped by the influx of mass, angular momentum, and energy from the surrounding disk. As matter in the accretion disk spirals inward, it undergoes dramatic compression and heating. Friction and magnetic turbulence within the disk convert gravitational energy into radiation, making accretion disks among the brightest sources in the universe. However, not all matter radiates away. A significant portion crosses the innermost stable circular orbit, ISCO, and plunges past the event horizon. This inflowing matter directly increases the mass and angular momentum of the black hole, expanding the horizon and altering its geometry in subtle ways. The inflow of angular momentum is particularly significant. As rotating matter falls into the black hole, it can spin the black hole up, increasing its spin parameter. This process, known as spin-up, alters the shape of the event horizon, flattening it at the poles and extending it at the equator. A maximally spinning black hole, or Kerr black hole, has a horizon that differs markedly from that of a non-rotating Schwarzschild black hole. The interaction between the accretion disk and the horizon is thus a dynamic feedback loop. The disk feeds the black hole, and the evolving black hole reshapes the surrounding disk environment. Additionally, magnetic fields in the accretion disk have a profound influence on the horizon. The intense turbulence in the disk, often described by the magnetorotational instability, MRI, generates strong magnetic fields that can thread the event horizon itself. These fields not only influence the accretion flow but also serve as channels for extracting rotational energy from the black hole, a mechanism central to jet formation. The Blandford's-Najek process, for instance, taps into the black hole's spin via magnetic fields anchored in the horizon, converting rotational energy into relativistic jets that blast out into space. These magnetic interactions also introduce time-dependent phenomena. As magnetic field lines reconnect or twist around the black hole, they generate flares, quasi-periodic oscillations, and variability in emission. Such fluctuations can propagate into the horizon, altering the geometry and energy density at the boundary. The horizon is not a static surface, but a constantly shifting interface responding to external inputs. These dynamics may be key to understanding phenomena like rapid X-ray flares and transient bursts from active galactic nuclei. The accretion disk also affects the thermodynamic state of the event horizon. As matter plunges into the black hole, it carries entropy. According to the laws of black hole thermodynamics, the surface area of the event horizon corresponds to entropy, and thus must increase when additional entropy is absorbed. The disk, by funneling in hot, chaotic matter, accelerates the growth of horizon entropy and influences the black hole's thermodynamic evolution. This entropic interaction leads to another fascinating point: the possibility that the horizon acts as a kind of thermal membrane, encoding information about the infalling matter. In some interpretations of the membrane paradigm, the event horizon behaves like a two-dimensional fluid with viscosity, conductivity, and temperature. The accretion disk, supplying heat and perturbations, stirs this fluid, causing ripples, shear flows, and possibly even turbulence on the horizon's effective surface. Another subtle effect arises from the frame dragging caused by spinning black holes. The spinning horizon drags spacetime around with it, twisting the inner parts of the accretion disk. This lens-stirring precession leads to warps and oscillations in the disk, which in turn feed back into the horizon via the dynamics of infalling matter. Observationally, this results in quasi-periodic signals in X-ray binaries and can help measure black hole spin. Relativistic effects near the horizon also allow parts of the accretion disk to orbit at incredible speeds. The innermost regions of the disk may complete hundreds of orbits per second, releasing radiation that is strongly redshifted and bent by gravity. This creates the characteristic broad iron lines in X-ray spectra. But more than that, these high-energy regions constantly interact with the event horizon, contributing not only mass and energy, but also imprinting structure into the geometry of the horizon via general relativistic effects. These interactions may also play a role in the generation of gravitational waves. While much of gravitational wave astronomy focuses on black hole mergers, theoretical work suggests that disturbances in accretion flows, such as clumps or magnetically driven instabilities, could also perturb the horizon and generate gravitational radiation. Though much weaker than merger signals, these waves could carry detailed information about horizon dynamics and accretion behavior. Over long periods, accretion disks are responsible for the majority of black hole growth in the universe. Supermassive black holes at galactic centers may have grown from stellar mass seeds to billions of solar masses largely through sustained accretion. In this process, their horizons have expanded by vast amounts, driven by the continuous flow of matter through the disk. Each accreted particle slightly enlarges the event horizon and deepens the gravitational well, making the black hole more massive and more influential. Furthermore, the structure of the accretion disk determines how efficiently a black hole can grow. Thin, radiatively efficient disks can allow for fast accretion, while thick, radiatively inefficient flows may trap radiation and slow down growth. The nature of the disk, its density, temperature, and magnetic structure, therefore plays a decisive role in how rapidly the horizon grows and how it responds to infalling matter. The interaction between accretion disks and event horizons may also influence the stability of black holes. In certain simulations, feedback from the disk via magnetic or radiative pressure can lead to temporary halts in accretion, or even episodic ejections of material. This feedback modulates the rate of horizon expansion and introduces quasi-cyclic behavior in horizon dynamics. The horizon becomes a boundary not just for collapse, but for a dynamic conversation between spacetime and matter. There is also growing interest in whether accretion disks could play a role in probing quantum gravity effects at the horizon. Some theories suggest that quantum structure near the horizon might leave imprints in the behavior of the innermost accretion flow, such as echoes, delays, or anomalous variability. Advanced X-ray and radio observations of disks may one day detect such features, offering empirical windows into physics beyond general relativity. In numerical relativity, simulations of black holes with realistic accretion disks have revealed complex, evolving horizon geometries. These simulations show the horizon deforming under the stress of incoming mass, twisting under magnetic tension, and pulsating in response to dynamical forces. The event horizon, though often portrayed as a smooth surface, is in fact an active, nonlinear object molded by its environment. In summary, the impact of accretion disks on horizon dynamics is vast and multifaceted. Far from being passive feeding structures, accretion disks energize, spin up, reshape, and thermodynamically evolve black holes through their intimate contact with the event horizon. The disk and the horizon are entwined in a gravitational and quantum relationship that defines the life cycle of black holes and may ultimately unlock the deepest secrets of gravity, spacetime, and quantum mechanics. The possibility of Planck-scale physics at the horizon. At the boundary of a black hole, where gravity becomes overwhelming and spacetime warps beyond classical understanding, lies the tantalizing possibility that the laws of physics break down and give way to Planck-scale phenomena. The Planck scale, characterized by the Planck length, 1.6 times 10 superscript 3 meters, Planck time, 5.4 times 10 seconds, and Planck energy, 1.2 times 10 superscript 1 GeV, represents the realm where quantum mechanics and general relativity intersect. Nowhere in the universe are conditions more suitable for accessing this realm than at or near the event horizon of a black hole. At macroscopic scales, general relativity treats the event horizon as a smooth, featureless surface. But when examined through the lens of quantum gravity, this image becomes suspect. Classical descriptions assume a continuous fabric of spacetime, but quantum theory suggests that this fabric is granular, discrete, or fundamentally probabilistic at scales approaching the Planck length. Near the event horizon, tidal forces become so intense and spacetime curvature so extreme that even infinitesimal differences can lead to divergent outcomes, making the classical model of the horizon incomplete. One key concept that emerges from Planck-scale speculation is the idea that the event horizon may not be a true geometric surface, but a region of intense quantum activity. Quantum fluctuations, normally minuscule, could become amplified by gravitational curvature, creating a dynamic, foam-like structure instead of a smooth horizon. This, quantum foam, could consist of virtual black holes, wormholes, or even topologically non-trivial distortions that flicker in and out of existence on Planckian timescales. Several theoretical frameworks aim to describe this exotic behavior. String theory, for example, posits that all particles are vibrational modes of fundamental strings. At the Planck scale, these strings can become excited in extreme ways, especially near horizons, where their energies approach the string scale. In this view, the event horizon could be a seething cauldron of string interactions, brane fluctuations, and extended quantum objects that defy classical geometry. The smooth event horizon of general relativity may simply be a large-scale approximation of this chaotic underlying structure. Loop quantum gravity offers a different picture. It suggests that spacetime itself is quantized and composed of discrete chunks, or spin networks, which define the geometry. In this view, the event horizon is a stitched-together mosaic of quantized area elements. The surface area of a black hole grows in quantized steps, and the event horizon is composed of a vast number of microscopic patches, each carrying a tiny bit of area, on the order of the Planck area. As matter crosses the horizon, it interacts with these elements, possibly transferring or altering quantum information. These quantum elements have thermodynamic implications. If the event horizon consists of Planck-scale degrees of freedom, then black hole entropy, famously proportional to the horizon's surface area, must be a count of these microstates. This idea is central to the holographic principle, which posits that all the information about a volume of space can be encoded on its boundary. Near the horizon, where gravity dilates time and amplifies energy, these microstates become dynamically active and potentially observable through high-energy phenomena. One of the most significant consequences of Planck-scale physics at the horizon is the firewall paradox. According to certain interpretations of black hole evaporation, an observer falling into a black hole would encounter a region of high-energy particles, called a firewall, at the horizon, violating the equivalence principle. This paradox arises from attempting to reconcile unitarity, quantum information conservation, general relativity, and quantum field theory. The presence of such a firewall would imply that Planck-scale physics violently disrupts the smooth horizon, replacing it with a seething quantum barrier. Another possibility is that the black hole horizon may harbor Planck-scale remnants of the matter it absorbs. In models where information is not lost but stored, it could be encoded in subtle quantum gravitational modes near the horizon, perhaps in the correlations between entangled particles or in deviations from semi-classical predictions. These Planck-scale structures might hold the key to resolving the information paradox by acting as long-term memory banks of everything the black hole has swallowed. Quantum entanglement across the horizon also gains new significance at the Planck scale. Normally, the vacuum state near the horizon is entangled between the interior and exterior regions. If Planck-scale physics modifies this structure, then the entanglement could be disrupted, leading to measurable deviations in Hawking radiation. Such deviations might reveal information about the black hole's interior or signal the breakdown of semi-classical assumptions. Planck-scale physics could also enable new types of phenomena that defy current understanding. For instance, mini-wormholes or microscopic causal bridges could form transiently at the horizon, allowing for quantum teleportation of information or particles in ways that skirt classical causal structures. These phenomena remain speculative but are mathematically plausible within certain quantum gravity frameworks. Their existence would fundamentally alter our perception of event horizons, not as absolute barriers, but as fluctuating, semi-permeable boundaries shaped by quantum geometry. Recent advancements in observational astronomy, particularly through instruments like the Event Horizon Telescope and gravitational wave detectors, may eventually offer indirect tests of Planck-scale physics. For example, echoes, in gravitational wave signals, tiny deviations following black hole mergers, have been hypothesized as signatures of Planck-scale structure at the horizon. While no such echoes have been conclusively detected, the possibility remains open and is the subject of intense investigation. Another concept closely tied to Planck-scale behavior at the horizon is the idea of fuzzballs and string theory. Rather than having a singularity surrounded by an empty horizon, a fuzzball is a configuration where the black hole is composed entirely of strings and branes that fill the volume up to the would-be horizon. These fuzzballs exhibit no horizon in the classical sense but instead have a complex, quantum surface that mimics a black hole's exterior while resolving the interior singularity problem. The transition between classical and quantum descriptions of the horizon is not just a matter of scale, it could involve a phase transition in spacetime itself. Just as water changes phases from liquid to gas, spacetime near the Planck scale may transition from smooth to discrete, or from geometric to algebraic. The horizon could be the site of such a phase change, governed by parameters like curvature, entropy, or quantum entanglement. This phase transition could also relate to emergent gravity theories, which argue that gravity is not fundamental but emergent from quantum information or thermodynamics. In this view, the event horizon is a manifestation of collective behavior at the Planck scale. Its properties, area, entropy, surface gravity, are akin to thermodynamic quantities that emerge from more fundamental microscopic rules. There are also implications for time itself. In some theories, time may become fuzzy or lose meaning at the Planck scale. Near the horizon, where gravitational time dilation becomes extreme, Planck-scale fluctuations could blur the very concept of a consistent timeline. This temporal ambiguity could influence the behavior of infalling matter and outgoing radiation, introducing non-local correlations or acausal effects. Ultimately, exploring the possibility of Planck-scale physics at the horizon brings us closer to a unified theory of quantum gravity. Whether through string theory, loop quantum gravity, or some future theory yet to be discovered, the event horizon may serve as the natural laboratory where the deepest laws of reality are revealed. The smooth veil described by general relativity could, under the scrutiny of quantum theory, unravel into a chaotic and vibrant quantum surface, forever reshaping our understanding of black holes and spacetime itself. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.